In October 2017, the solar system was visited by something fast, faint, and utterly unexpected. It wasn't a comet or an asteroid like the ones we were used to seeing. It came from outside our solar system, spinning oddly and behaving in ways that didn't make sense. Scientists named it Oumuamua, which means a messenger from afar arriving first in Hawaiian. It was the first known interstellar object to visit us, and it had no visible tail, no gas emissions, and a very strange shape. Even more puzzling, it sped up slightly as it left the solar system, and no one could fully explain why. Was it a natural object, or was it perhaps artificial? Let's follow Oumuamua, examine the science and speculation it inspired, and explore what it means for our understanding of the universe, and maybe even life beyond Earth. Beyond borders, interstellar visitors. For centuries, astronomers have studied comets and asteroids. These small objects, mostly made of rock, metal, or ice, are considered remnants from the birth of our solar system. They orbit the Sun, some with long sweeping paths that take hundreds or even thousands of years to complete. While fascinating in their own right, native comets and asteroids follow patterns we've come to understand. Their compositions are fairly predictable, and their movements, though sometimes erratic, can usually be traced back to gravitational interactions with planets or the Sun itself. Interstellar objects don't belong to our solar system. Their speeds, angles of approach, and chemical makeup often don't match anything we've seen before. While comets from our own system may swing around the Sun and return centuries later, interstellar objects come from the unknown. They enter and leave quickly, unbound by the Sun's gravity, giving us only a short window to study them. The first time we found one of these objects was in 2017, when astronomers in Hawaii spotted something unusual moving through the solar system. From the moment it was detected, Oumuamua refused to fit into any familiar category. It wasn't behaving like a normal asteroid, and it didn't look or act like a comet. In fact, it wasn't clear what it was at all. Unlike asteroids, which are usually slow-moving and gravitationally tied to the Sun, Oumuamua was fast, much faster than anything native to the solar system. It entered at such a high speed that astronomers knew right away it couldn't have originated here. Its trajectory showed it was passing through, not staying. And when it left, it did so on a path that meant it would never return. That alone made it special. But as scientists observed it more closely, they found even stranger things. Most comets, when they get close to the Sun, begin to heat up and release gas and dust in a process called outgassing. This creates the glowing tails we see in the night sky. Outgassing also causes a comet to accelerate slightly as the gas pushes it forward, like steam escaping from a kettle. But while Oumuamua did accelerate as it moved away from the Sun, it didn't produce the expected cloud of gas or dust. There was no visible coma, no tail. It moved in ways that made sense for a comet, but without the signs that make comets easy to spot. It was like watching someone walk across a snow-covered field, leaving no footprints behind. That puzzle set off a wave of theories. Was it a comet made of unusual materials? Was it a fragment of a larger object? Was it something more exotic? Perhaps even artificial? Scientists approached these questions with both caution and curiosity. While most leaned toward natural explanations, the fact remained this was something we had never seen before. One of the most interesting things about Oumuamua was its shape. Based on how its brightness changed over time, astronomers guessed it was either long and cigar-shaped or flat like a pancake, tumbling end over end as it moved. Either way, its proportions were unlike any known asteroid or comet. Its surface was reddish, possibly due to long exposure to cosmic radiation in interstellar space. But its exact makeup and origin remained a mystery. Before Oumuamua, the idea of studying objects from other star systems seemed nearly impossible. We assumed such visitors could exist, but we'd never had the chance to see one. Once we did, we realized just how much we didn't know. These objects carry chemical fingerprints of the environments they came from. By studying them, we might understand what other solar systems are made of, how they form, and whether the same ingredients that shaped our own planets are common elsewhere. These interstellar visitors remind us that our solar system is not isolated. Just as we send spacecraft out into deep space, other star systems may eject pieces of themselves into the cosmos. Some of these fragments may travel for millions or even billions of years before reaching us. When they arrive, they bring with them clues, not just about distance and speed, but about time and origin. In a way, they are messengers, just like Oumuamua's name implies. A new frontier, why Oumuamua defies solar system expectations. Oumuamua's journey through our solar system was brief, but it left a long trail of questions behind. One of the first things that caught astronomers' attention was its speed. Most objects that orbit the Sun, including planets, moons, and comets, move along predictable paths. These orbits are shaped by the Sun's gravity. Some of the fastest comets, like those coming from the distant Oort cloud, can reach speeds of 40 to 50 kilometers per second as they fall inward toward the Sun. Oumuamua came in much faster. As it passed through the solar system, it traveled at about 87 kilometers per second relative to Earth. More importantly, even after it curved around the Sun, it didn't slow down enough to be captured. Instead, it continued on a straight path outward, escaping entirely. Its incoming path also revealed something else. Rather than approaching from the ecliptic, the flat plane where the planets orbit, Oumuamua came in at a steep angle, from above. This kind of approach is unusual for anything native to our solar system, but it fits the pattern of something coming from interstellar space. Once it curved around the Sun, it exited in a completely different direction, one that again didn't match typical solar system objects. Its path was a hyperbola, not a closed ellipse. That kind of shape means it was never going to return. Astronomers quickly turned their telescopes toward the object, hoping to learn more before it vanished. They measured how the sunlight reflected off its surface and tracked its motion hour by hour. What they found raised even more questions. Normally, when comets get close to the Sun, their icy surfaces begin to vaporize, and they outgas, which can also push the comet slightly off course. Oumuamua's path showed a slight but clear acceleration, but without any visible tail or glow. It looked solid and dry, with no sign that anything was evaporating from its surface. If it was accelerating like a comet, where was the gas? If it wasn't outgassing, what was causing the change in speed? Some theories suggested that it might be made of hydrogen ice, a substance that would evaporate without leaving visible traces. Others guessed it might be a fragment of nitrogen ice, similar to the surface of Pluto. But these ideas had problems too. Hydrogen ice is so fragile that it likely wouldn't survive a long journey through space. Nitrogen ice seemed unlikely to form the kind of shape Oumuamua had. The shape itself became another source of debate. As the object tumbled through space, the amount of sunlight it reflected changed dramatically, sometimes getting bright, then quickly dimming. This suggested it wasn't round, but elongated. The brightness varied by a factor of 10, which is more than any known asteroid or comet. Most space rocks don't show that kind of variation unless they have very unusual shapes. This led to more questions. What kind of natural process could create an object shaped like that? Was it a piece of a shattered planet? Could it be a thin, flat object that had been worn down by cosmic dust or radiation over millions of years? Or was it something else entirely? No known object in our solar system matched all of Oumuamua's characteristics: its speed, its path, its lack of tail, and its odd shape. Some scientists suggested that maybe our tools weren't sensitive enough. Perhaps it did release gas, just in amounts too small to see. Others began to wonder if it might represent a new type of object altogether, something we had never seen before because it had never come this close. A few voices even proposed that it might be artificial, a piece of alien technology, perhaps a probe or a piece of space debris from another civilization. This idea caught the public's attention quickly, especially when it came from well-known scientists. They pointed to the unusual acceleration and lack of visible explanation. Could radiation pressure from sunlight have pushed it? If so, it would need to be very thin, perhaps even a light sail, the kind of structure humans have only begun to explore in theory. Most scientists were cautious about this suggestion. While they didn't rule it out entirely, they looked for other explanations. Still, the fact that such a discussion even took place showed just how strange Oumuamua truly was. It wasn't just that we didn't know what it was. It was that we didn't know how to fit it into any existing category. All of this happened over just a few weeks. Oumuamua was first detected in October 2017. By early 2018, it was already too far away to study in detail. Its speed carried it beyond the reach of even our most powerful telescopes. The data we gathered came from a short window, a matter of days really, and much of it left more questions than answers. After Oumuamua, interstellar visitors became real, and with that reality came a new sense of urgency. What other objects might be passing through our solar system unnoticed? How many have we missed? And what might they tell us about the planets, stars, and systems beyond our own? The precursor search, how we learned to spot cosmic drifters. Before the discovery of Oumuamua, astronomers had long been watching the sky for small objects. These surveys were built to protect Earth from potential asteroid collisions and to help us understand the leftovers of our solar system's formation. But even though these programs were highly advanced, none of them had caught anything quite like Oumuamua. That wasn't because these objects didn't exist. It was because we weren't looking in the right way. In the early 2000s, one of the most important sky surveys was called LINEAR, the Lincoln Near-Earth Asteroid Research Project. Based in New Mexico, Linear used telescopes equipped with sensitive cameras to scan the skies night after night. Its main goal was to find near-Earth objects, especially those that could pose a threat to our planet. Over time, Linear discovered thousands of new asteroids and dozens of comets, helping scientists map the space around Earth more thoroughly than ever before. But Linear, like most surveys of the time, was focused on objects moving in ways that fit within solar system dynamics. Its detection software was tuned to look for things that followed expected paths, objects orbiting the Sun in ellipses, moving at speeds and angles that made sense for something born within our own star's influence. Anything that didn't fit that mold could easily be missed or discarded as noise. This wasn't a flaw in the system, it was a result of our assumptions. For decades, astronomers believed that interstellar objects might exist, but they were thought to be extremely rare. Most were expected to be tiny, dark, and fast, making them almost impossible to detect with older instruments. And since no confirmed interstellar visitor had ever been seen, there was little pressure to design systems specifically to catch them. Another major survey system was the Catalina Sky Survey, based in Arizona. Like Linear, Catalina was focused on near-Earth asteroids. Its wide-field telescopes covered large portions of the sky, capturing thousands of images each night. Catalina used powerful computers to compare images and identify moving objects, flagging anything that shifted position against the background stars. Catalina improved our ability to find and track smaller objects, and over time, it helped expand our list of known asteroids significantly. But again, its focus was mostly local. Objects like Oumuamua weren't the main priority. If such an object had passed by Earth during the early years of Catalina or Linear, it's very likely we wouldn't have noticed it at all. Both surveys relied on algorithms built to expect patterns. But interstellar visitors don't follow those patterns. This means that unless we're looking in just the right place, at just the right time, they can pass by completely unnoticed. These limitations became clear after Oumuamua's visit. For many astronomers, this was a turning point. Our approach hadn't kept up with the changing needs of science. The Pan-STARRS telescope in Hawaii was the first to detect Oumuamua. Unlike Linear and Catalina, Pan-STARRS had a broader mission. It was designed not only to track near-Earth asteroids, but also to observe supernovae, variable stars, and even galaxies. It had a wide field of view and highly sensitive cameras, allowing it to scan large areas of the sky quickly. It was also set up to spot transient objects, things that appear suddenly and disappear just as fast. Pan-STARRS used updated software that could better handle odd movements and strange brightness patterns. So when Oumuamua entered the solar system, Pan-STARRS was able to pick it up before it got too far away. But even then, it was a narrow catch. The object was already on its way out by the time it was spotted. Observers had just a few weeks to study it before it faded into the distance, too dim to track. That close call made scientists realize something important. If we wanted to find more of these objects, we'd have to build systems that were not only better, but smarter. The old ways of watching the sky weren't enough. We needed tools that could detect faster, stranger, and rarer things. We needed to stop assuming that all space rocks belong to the solar system. The lesson was clear. If we had nearly missed Oumuamua, how many more had slipped through the cracks of our surveys, moving too fast or too strangely to be recognized? It was likely more than a few. Software began to be rewritten to allow for less predictable paths. Detection systems were adjusted to hold on to objects that moved unusually fast or didn't follow known orbital patterns. Astronomers started working more closely with teams developing artificial intelligence, hoping to teach machines how to spot things that don't fit the mold. At the same time, newer and more powerful telescopes were already being planned. The Vera C. Rubin Observatory, set to begin operations in the coming years, promises to revolutionize our view of the sky. With its massive mirror and cutting-edge imaging system, it will be able to scan the entire visible sky every few nights, catching even the faintest moving objects. This telescope will be able to find fast transients that might have gone unnoticed in earlier years. Discovery Night, the first glimpse of Oumuamua in Pan-STARRS data. Pan-STARRS stands for Panoramic Survey Telescope and Rapid Response System. Its main telescope, Pan-STARRS 1, uses a powerful digital camera and wide field of view to scan the night sky. Every clear night, it takes images of huge sections of space, collecting data that is then processed by computers at the Institute for Astronomy, part of the University of Hawaii. The discovery began like most nights at the observatory. The telescope swept through its assigned sections of the sky, capturing long exposure images every few minutes. These images were then run through a special set of software tools built to spot changes, tiny differences in position, brightness, or shape that might suggest movement. Each night, thousands of moving points of light are recorded and compared to known objects. Most are already catalogued: Earth-crossing asteroids, long-period comets, or man-made satellites. That evening, a small, fast-moving point of light was flagged by the automated detection system. It showed up in 4 images taken over the course of about 40 minutes. The object moved in a straight line and appeared as a faint trail in the data, something fast enough that its motion was visible even in the span of a short exposure. The telescope's software didn't recognize it as a known object, so it was flagged as a new discovery, a candidate for further observation. When a potential new object is found, the Pan-STARRS pipeline sends the information to human reviewers. astronomers train to scan through fresh detections and decide what's worth following up. That night, the detection was passed to Rob Werrick, a postdoctoral researcher working at the University of Hawaii. It was his job to check whether the new object was real or just an error, an artifact of image noise, or perhaps a reflection, or even a passing satellite. Werrick reviewed the data and quickly realized something strange. The object's motion didn't fit the usual pattern, which alone would be odd, but there was more. When Werrick tried to match it with known objects in the Minor Planet Center database, he found nothing. To confirm that it wasn't a one-time glitch, Werrick checked earlier images from the same telescope. Pan-STARRS stores huge amounts of sky data, and sometimes objects are captured in older images without being noticed at the time. After some searching, he found the object in data from the previous night. The position matched, and the motion was consistent. That was the confirmation he needed. It was a real object. At this point, the object still had a temporary name, P10EE5V. It had not yet been officially confirmed, but the team suspected it was something special. Werrick contacted his colleague Marco Micheli at the European Space Agency, who was observing from Tenerife in the Canary Islands. Using Micheli's data, the team could track the object from a slightly different angle, helping to pin down its path through space. When the two data sets were combined, the picture became clear. This object was not bound to the Sun. It was on a hyperbolic path. The numbers showed a velocity that exceeded the solar escape speed. It was not from here and was simply passing through. This realization set off a wave of excitement in the astronomy community. Within hours, the object was reported to the Minor Planet Center, which oversees the global tracking of small solar system bodies. There, it received a more formal name, a /2017 U1. The A stood for Asteroid 2017 marked the year, and the U1 meant it was the first such discovery in the second half of October. But within days, it became clear that this was not just another asteroid. As more data came in from telescopes around the world, its orbit was refined. The eccentricity of its path, a number that describes how stretched out an orbit is, was over 1.2. Anything over 1 is not bound by the Sun's gravity. For reference, most comets from the Oort cloud have eccentricities just slightly over 1 due to the Sun's pull. This object's number was well beyond that. It was the most extreme orbit ever recorded for a natural object. At the same time, astronomers were scrambling to point other telescopes at it. Its brightness was fading fast, and every day it moved farther from Earth. They used instruments across the globe, optical telescopes to measure its shape and brightness, radio telescopes to listen for any signals, and infrared sensors to detect heat. Teams worked through the night, swapping data in real time, trying to learn as much as possible before it slipped away. Within days, the International Astronomical Union gave it a permanent name, Oumuamua. What made the discovery night so remarkable was the blend of machine precision and human insight. The Pan-STARRS software did its job, catching a fast-moving point of light. But it was a person, Rob Werrick, who looked at the data and asked the right questions. It was the collaboration between researchers across oceans that turned a blurry streak into one of the most important astronomical discoveries of the decade. The workflows of Pan-STARRS are designed for speed and volume. Each night brings terabytes of data, and the software must sift through it all in hours. Objects are tracked, catalogued, and passed through automated filters. But the real power lies in the handoff, from software to scientist. It's in that space, between code and curiosity, that discoveries like Oumuamua happen. Shape and spin, unraveling Oumuamua's unusual axial ratio. Most asteroids and comets in the solar system are roughly round, or at least potato-shaped. Their axial ratios, the comparison between their longest and shortest dimensions, are usually around 2 or 3 to 1. That means they might be twice as long as they are wide. But the light curve of Oumuamua pointed to an axial ratio of at least 6:1, and possibly even as much as 10:1. That was unprecedented. Nothing else in the solar system is known to have such proportions. Even the most oddly shaped small bodies, like some contact binary asteroids, don't come close. And while a long, thin shape might sound simple, it's actually hard to maintain in space. Over time, collisions and thermal stress tend to break down fragile structures. So if Oumuamua had travelled between stars for millions or even billions of years, how had it held together? Most small bodies rotate in a simple pattern, like a spinning top. Their spin axis stays stable, and they repeat the same motion over and over. But Oumuamua appeared to be tumbling, moving in a non-repeating, wobbling pattern that suggested it wasn't rotating around a single, clean axis. This kind of spin is called non-principal axis rotation, or tumbling for short. Tumbling can happen when an object gets a jolt, such as from a collision or a strong gravitational pull. Once an object starts tumbling, it stays that way unless some force acts to calm the motion down. In the case of Oumuamua, its tumbling motion was stable, which meant it had likely been spinning that way for a long time. That fact, combined with its strange shape, hinted at a violent past, perhaps being ejected from its original star system by a powerful gravitational interaction, or even torn apart and reshaped before being flung into space. The light curve analysis also helped narrow down the size of Oumuamua. Since we couldn't see it directly, its size had to be inferred from how bright it was and how reflective its surface might be. If it was highly reflective, like a shiny metal, it could be smaller. If it was darker, like coal or soot, it would need to be larger to reflect the same amount of light. Based on its brightness and the lack of any visible dust or gas, scientists estimated that Oumuamua was likely no more than a few hundred meters long, possibly around 100 to 200 meters. Its width, depending on the assumed shape, could have been just a few tens of meters. That would make it thinner than most known asteroids, especially if it had a flat disc-like shape. These measurements carried uncertainty, but all pointed to a single conclusion. This was not a familiar kind of object. One theory proposed that it might be a fragment of a larger object, possibly a piece broken off during the formation or destruction of a planet in another system. Another idea was that it had been shaped over long stretches of time by the erosion of interstellar dust and gas. As it passed through the space between stars, tiny particles could have slowly chipped away at its surface, wearing it down into a streamlined form. The more astronomers studied the light curve, the more questions it raised. Why had this shape never been seen before? Could we expect more objects like this in the future? Were we simply missing them until now, or was Oumuamua a true rarity, an odd piece of debris that happened to pass through our part of the galaxy? We had never expected an object like this, and we weren't fully prepared to study it when it arrived. The data we did collect came in a rush, driven by urgency and limited by distance. But from that faint flicker of light, we learned that space can still surprise us. Spectral secrets: what light tells us about its surface. Every object in space reflects sunlight a little differently, depending on what its surface is made of. Some objects reflect more light in the red part of the spectrum. Others reflect more in the blue. Some absorb most of the light and appear very dark. By measuring how that light is spread out across different wavelengths, astronomers can guess what materials are on the surface, even from millions of miles away. One of the first things astronomers noticed was that Oumuamua's light was slightly red. Not extremely red, but more red than the sun's light. That's important, because it tells us something about the surface. Many small bodies in our solar system, like comets, centaurs, and distant Kuiper Belt objects, have this kind of reddish color. It's usually caused by organic rich compounds on the surface that have been changed by long-term exposure to radiation. These compounds are often called tholins, complex carbon-based molecules formed by the breakdown and reformation of simpler chemicals under ultraviolet light or cosmic rays. This reddening effect takes time to develop. An object needs to be exposed to deep space conditions for millions of years to build up that kind of surface layer. So even though we didn't know where Oumuamua came from, its color told us it had been in interstellar space for a long time. But the reddish tone wasn't as deep as some distant solar system objects. That raised questions. Was it partly covered in different materials? Or had it been protected from radiation for some period of time and only recently exposed? Or maybe the angle at which we saw it made the color seem less intense than it actually was. The spectra also showed something else. There was no sign of water ice or common ices like carbon monoxide or carbon dioxide on the surface. This lack of icy signatures made scientists think its surface was either dry to begin with or had a thick crust that kept any ices trapped inside. If the surface was made of processed organics, those reddish tholin-like materials, it might have sealed the object, stopping the sun's heat from reaching whatever might lie below. That could explain why no gas or dust was seen, even though it passed fairly close to the sun. Another possibility was that Oumuamua had once been icy, but lost its outer layers long ago. Over millions of years, cosmic rays might have stripped away lighter materials and left behind a dense, carbon-rich shell. That shell would be tough and dark, able to survive another journey into a star system without releasing vapor. The reflectance measurements also help rule out other types of materials. Oumuamua didn't look like a metallic asteroid. Those types of objects reflect light in a very different way. They usually have a flatter, more neutral spectrum without the reddish slope. Metal-rich asteroids also tend to be brighter. Oumuamua, by contrast, was relatively dim. It didn't match the profile of silicate-rich asteroids either, the kind you find in the inner solar system. Those have specific absorption features caused by minerals like olivine and pyroxene. Oumuamua's spectrum didn't show those markers. Instead, its spectral signature placed it closer to the kind of material seen in the outer regions of our own solar system. That's where comets and other icy bodies form. It suggested that Oumuamua may have come from a distant region in another planetary system, perhaps a zone similar to our Kuiper Belt or Oort cloud. Still, there were oddities. Even though it shared some surface characteristics with comets, it behaved very differently. The surface might have been similar, but the inner structure, or the way the object was formed, could have been completely different. That was part of the mystery. Light told us only what was happening at the surface. It couldn't show us what was inside. Some scientists speculated that the reddish coating was only skin deep, and that the interior could contain different materials. Others wondered if Oumuamua was made of something we hadn't seen before. Maybe it had a high content of exotic ices that don't show up easily in spectra. One theory suggested that it could be made of molecular hydrogen ice, which would evaporate without leaving obvious chemical traces. But that idea faced problems of its own. Hydrogen ice is extremely delicate and would probably not survive the long trip through interstellar space. Trajectory analysis, backtracing, Oumuamua's origin. Finding out where Oumuamua came from was one of the first things astronomers wanted to do after it was discovered. If it had entered the solar system from another star, then tracing its steps back through space might give us a clue about which system it was born in. But this turned out to be a lot harder than it sounded. The first thing scientists had to do was figure out exactly how it was moving. From telescope images taken over a period of days, they calculated its position and speed. Once they'd figured those out, they tried to reverse it. This is called backtracing. It's like rewinding a movie. You take the object's current position and velocity, and then you run the numbers backward. You simulate how gravity from the Sun, planets, and even the galaxy itself would have affected it over time. You keep rewinding until you get to a point far outside the solar system, until you reach interstellar space. That's the basic idea. But in practice, it's very complicated. Space is full of moving parts. The Sun is not sitting still. It's orbiting the center of the galaxy, just like all the other stars. Every star has its own speed and direction. Some stars are in clusters. Some are alone. Some pass near us for a while, then drift away. So when you rewind Oumuamua's path, you also have to rewind the motions of thousands of stars at the same time. Astronomers use powerful simulations to do this. They rely on star catalogues like Gaia, which gives very accurate positions, distances, and velocities of stars near our solar system. These catalogues are essential because without knowing how stars were moving millions of years ago, there's no way to see if Oumuamua might have come near one. Scientists created a 3D model of the region around the Sun. They included the gravitational effects of the major stars within dozens of light years. They ran simulations where Oumuamua passed through this changing field of gravity. They looked for close encounters, moments in the past when its path might have come near a star. If it passed very close and slow to one, that could be a sign that it originated there. But if it flew past every star at high speed, or at great distance, then it likely wasn't born in those systems. The results were frustrating. No star stood out as the clear source. Most encounters happened too far away to mean anything, many light years apart. Others were close, but only in space, not in time. A star might have been in the right position, but it wasn't there when Oumuamua passed by. The timing didn't match up. One of the best candidates was a star called HIP 3757. It came within about 1.5 light-years of Oumuamua's backward path, but the speeds didn't align well. Another possibility was HD 292249. That star had a trajectory that almost lined up, but again, the timing and motion were not a perfect fit. There are a few reasons why it's so hard to pinpoint the origin. First, there's uncertainty in the data. Even small errors in the measurement of Oumuamua's speed or angle can make a big difference over millions of years. The same is true for the stars. We don't always know their exact motions in 3 dimensions. Some stars have unknown companions, like planets or other stars, that could affect their paths slightly. These small unknowns add up over time. Second, Oumuamua could have been ejected from its home system in a chaotic way. Imagine a planet-sized object swinging by a giant planet like Jupiter. The gravity can fling it out into space at high speed. This kind of gravitational slingshot is random and violent. It doesn't follow a neat or simple path. If Oumuamua left its home like that, then it's possible it has been wandering for a long, long time. In that case, its original star might not even be nearby anymore. Stars move a lot over time. They don't stay in fixed positions relative to each other. There's also the problem of how many stars we haven't catalogued. Gaia's database is vast, but it doesn't include every star, especially faint ones or those far from Earth. Oumuamua could have passed near a small, dim star we haven't measured yet. That would make it impossible to find the encounter using current data. Some researchers proposed a different approach. Instead of looking for the exact star, they looked for the general population of stars that matched the velocity of Oumuamua. They tried to figure out what kind of stellar environment would naturally produce an object moving the way it did. They compared it to stars in the local galactic disk. The idea was to treat Oumuamua not as a special case, but as a random sample from a large group. This helped put limits on its possible origin, but didn't give a precise answer. Others wondered if Oumuamua might have come from a disrupted system. Maybe it was part of a binary star system that broke apart. Or maybe it formed in a dense star-forming region, like a stellar nursery, and got kicked out early in its life. If so, the exact point of origin would be impossible to trace, because the original star may no longer exist, or may be unrecognizable due to stellar evolution. Despite all the effort, no one has found a smoking gun, a clear match between Oumuamua's incoming path and a specific star. Instead, what the trajectory analysis has done is remind us how big and dynamic our galaxy is. It is a swirling ocean of motion. Stars fly past each other. Systems change. Over millions of years, everything shifts. Astronomers still hope that future interstellar objects might offer better chances. If we catch one earlier, while it's still inbound, we can gather more data. If we can trace its motion with higher precision and compare it to improved star catalogues, we might get lucky. One day, we might catch an interstellar traveller whose path leads right back to a known star system. That would be a big step forward. Until then, Oumuamua remains a mystery. The object that came from beyond borders still keeps its true home to itself. Gravitational versus non-gravitational forces, the unexpected boost. When astronomers track a comet or asteroid, they rely on well-tested physics. Gravity is the main force at work. The Sun pulls on objects with a known amount of strength based on distance. Planets and moons can add smaller effects. Once you know the positions of these bodies and how heavy they are, you can predict where a comet or asteroid should go with amazing accuracy. These are Newton's laws in action. At first, Oumuamua seemed to follow this model. It entered the solar system at high speed, curved around the Sun, and began heading back out. Everything matched the math, until it didn't. As they collected more data, astronomers noticed something odd. Oumuamua was drifting slightly off course. This shift was extremely subtle, just enough to change its position by a small fraction over time, but it was real, and it wasn't random. The object seemed to be accelerating very gently, and the direction of that acceleration matched what you'd expect if it were being pushed slightly away from the Sun. For typical comets, this kind of behavior isn't unusual. Their outgassing pushes the comet slightly off its gravity-only path. These are called non-gravitational forces. Astronomers understand them well. They've even built them into the software that models comet paths. But Oumuamua had no visible tail, no gas cloud, and no coma. So why was it moving like a comet? To figure this out, scientists looked at how much acceleration was happening and in what direction. The numbers showed that the force was far beyond the level you'd get from something like radiation pressure alone. And because Oumuamua was already past its closest approach to the Sun when the force was strongest, it ruled out some obvious causes. That's when the speculation began. Some researchers suggested that Oumuamua might be made of ices that don't release visible gases. Others posited that Oumuamua might be extremely flat and thin. If that were true, then the Sun's radiation pressure could give it a large enough push. Photons carry momentum, and when they hit an object, they transfer a tiny amount of force. It's usually very small, but over long periods, it can add up. This is the same principle used in solar sails. For Oumuamua, the shape needed for this to work would have to be very strange, only a few millimeters thick, but many meters wide. How could a natural process create such a shape? Where would such a fragile object come from? And if it was artificial, who or what made it? Maybe interstellar objects come in more forms than we're used to. Maybe our understanding of comet activity needs to change. Maybe nature is more creative than we expect. To test these ideas, scientists went back to the data. They used infrared telescopes to search for signs of gas. They analysed how the brightness of Oumuamua changed over time to rule out hidden jets. They modelled how different materials would behave in the Sun's heat. Each test narrowed the list of possibilities, but didn't close the case. The object remained a puzzle. What scientists were left with was a small change in motion and no obvious cause. This taught astronomers something important. The next time an interstellar object is spotted, they need to act fast. Observations must begin earlier, before the object passes the Sun, when any unusual forces might be easier to detect and understand. Special attention should be paid to small changes in motion. because those can reveal the unseen forces at play. Dust-free propulsion. Lessons from comet-like behavior. When most comets approach the Sun, their icy surfaces begin to warm and frozen gases start to vaporize. These gases push outward from inside the body, escaping into space in jets. As they do, they also carry dust grains with them, tiny rocky particles that were trapped inside the ice. The result is a bright, glowing coma, often followed by a long dust tail. It's this combination of gas and dust that gives comets their striking appearance. But with Oumuamua, none of that happened. If anything was coming off the object, it wasn't carrying dust grains along with it. To understand why, scientists turned to models of comet behavior. They compared what happens when gas escapes along with dust versus when it escapes alone. In most comets, gas and dust work together. Gas jets do the pushing, but dust makes it visible. The dust also adds mass and structure to the coma and tail. Its interaction with sunlight is what produces the soft, glowing look we see in telescope images. It also helps trace the direction of motion and tells us about the physical makeup of the nucleus. In a dust-poor or dust-free outgassing scenario, everything looks different. When gas escapes without pulling along dust, it's much harder to see. There's no thick cloud, no sparkle, and no visual trace in normal photographs. The escaping gas is often invisible unless special instruments are used, tools that detect ultraviolet light or subtle chemical changes in the atmosphere. These kinds of events can go completely unnoticed in ordinary surveys. Oumuamua seemed to match that second category. If it was releasing gas, it wasn't dragging dust with it. That tells scientists something important about the surface and subsurface layers of the object. In comets like 67P/Churyumov-Gerasimenko, studied up close by the Rosetta spacecraft, the outer crust is full of grains and clumps, fine powder mixed with ice. When the ice sublimates, it pulls these grains loose. But if an object has gone through heating and cooling many times, or if its crust is made mostly of large ice crystals with very little trapped material, then dust might not be released at all. This idea led to the thought that Oumuamua might have a very different structure from most solar system comets. Its outer layer might be compact, even hardened. Repeated cycles of exposure to cosmic radiation between the stars could have changed the nature of the ice, driving away light volatiles and leaving behind a crust rich in heavier, more complex molecules. These types of surfaces are known to form in space. A hardened, carbon-rich surface like that could hold in gases until the object warmed up considerably. If the crust had become strong enough to trap gases without breaking apart, then sublimation might happen in a slow, controlled way. Gas leaking out through tiny pores or cracks, instead of bursting forth in jets. This would result in very weak thrust, but it could still add up to a measurable acceleration, especially for a small, lightweight object like Oumuamua. At the same time, if there was little or no dust mixed into the crust, there would be nothing to scatter sunlight or create a visible tail. This is what makes the idea of dust-free propulsion so intriguing. It could explain why astronomers didn't see a coma, even while the object showed signs of changing speed. It might also explain why the light curve stayed so smooth, no clouds of particles spinning off or breaking the object's symmetry. But this theory also raises questions. Why would Oumuamua be so different from the comets we know? One possibility is that it came from a very different kind of star system. If it formed around a smaller, colder star, it might have spent billions of years at very low temperatures. That kind of environment could allow unusual ices to form, not common in the outer solar system. These materials might sublimate differently than water ice. Some might even vaporize without disturbing the surrounding crust. Another possibility is that Oumuamua was once an active comet, but after being ejected from its home system, it floated through interstellar space for millions of years. Over such long timescales, radiation can turn ice into complex organic matter, gradually building up a dense crust. What's left? is a hardened layer that only allows the smallest molecules to seep out when warmed. In other words, Oumuamua didn't behave like a dusty comet, but it may still have behaved like a comet in a quiet, dry form. It may have been made of unfamiliar materials or aged in an unusual way. It may have lost its dust long ago, or it may have formed without much dust in the first place. Any of these possibilities would mark a sharp contrast from the icy, dusty bodies that make up our own comet population. If Oumuamua is typical of interstellar objects, if most of them are dry, dark and dust-free, it means they could be passing through our solar system more often than we think. Without a visible coma or tail, these objects would appear very dim. Only if they show unusual motion or reflect strange patterns of light would we know to look closer. Alien probe. Hypothesis: the light sail conjecture. The idea that Oumuamua could be something other than natural, a piece of alien technology, is one of the most exciting and controversial suggestions to come from its visit. The most well-known version of this idea came from Harvard astronomer Avi Loeb and his colleague Shmuel Bialy. In 2018, they published a scientific paper that took a different path than others. Instead of treating Oumuamua like a comet or asteroid, they looked at the possibility that it might be something artificial, specifically a solar sail. A solar sail is a real concept in engineering and physics. Unlike rockets, which use fuel, solar sails use nothing but light. Several versions have already been tested around Earth. Projects like Icaros and LightSail have shown that thin sails can adjust speed and direction in space using sunlight alone. Loeb's paper didn't claim that Oumuamua was definitely a light sail. Instead, it showed that if you assume it is, then many of the object's strange features start to make sense. One example was the acceleration, as discussed before. The light sail idea also had something to say about the object's shape. A wide, flat shape would be a better match for a sail. It would catch more light and respond more efficiently to pressure. The tumbling motion of the object might even be explained as a leftover spin from an earlier maneuver, or the natural result of travelling through space for a long time. If Oumuamua was truly a light sail, then where did it come from, and why was it here? One idea is that it could be a piece of debris, space junk left behind by an alien civilization. Just as Earth is filling space with old satellites, boosters, and broken equipment, it's possible that other civilizations might have done the same. If so, Oumuamua might be the interstellar equivalent of a drifting sailboat mast, long abandoned but still catching the wind. Another possibility is that it was a working probe, a kind of scout sent out to collect information. This idea is harder to support since no radio signals, energy pulses, or navigation changes were detected. Radio telescopes listened for days after the discovery, but picked up nothing. Still, the lack of signal doesn't prove the object is natural. It only shows that if Oumuamua was artificial, it either wasn't communicating or was doing so in a way we could not detect. Many astronomers pushed back on the light sail theory. They argued that extraordinary claims need extraordinary evidence. They pointed out that natural objects can still act in strange ways, especially when we only get limited data. Oumuamua was only visible for a short time. No telescope got a close-up image. Most of what we know comes from a faint dot of light moving quickly across the sky. From that, scientists had to guess its shape, its spin, its makeup, and its path. Many said it was too soon to say anything for certain, especially something so dramatic. Others welcomed the idea, not as a final answer, but as a reminder to keep an open mind. The truth is, Oumuamua was something new, and possibly something we weren't prepared to explain using our usual tools. In that context, asking whether it might be artificial was not just science fiction, it was a scientific question. The light sail theory helped open that discussion. It encouraged people to think beyond known models and explore ideas that might seem unlikely, but not impossible. It also brought attention to the growing field of technosignature research, looking not just for alien life, but for signs of alien technology. If another civilization had built light sails and launched them into space, those sails might drift for eons, crossing the void between stars. One of them might pass through our solar system one day, just as Oumuamua did. No physical proof of such a sail has been found. Oumuamua is now gone, but the idea it left behind, a possibility that something drifting silently through space might not be a rock or a comet, but a machine, continues to raise questions. If Oumuamua was built, then who built it? Where did it come from? And could there be more like it, still waiting to be seen? Asteroid AIs, self-replicating machines hidden in plain sight. The idea that some objects drifting through space might not be natural at all, but machines in disguise, has started to gain more attention, especially in the wake of Oumuamua's visit. While many scientists still lean toward natural explanations, others are beginning to ask new kinds of questions. What if something that looks like an asteroid or a comet isn't one at all? What if it's a machine, built to travel, observe, or even make copies of itself, and its rocky appearance is only a mask? This idea connects to a concept that's been around for decades in science and engineering circles: self-replicating machines. The basic idea is simple but powerful. If a machine could gather raw materials and use them to make copies of itself, then it could spread widely through space without outside help. It wouldn't need fuel launches or radio guidance from its home world. It would be independent. Over time, it could build new versions of itself again and again, hopping from one asteroid or moon to the next. This would let it explore star systems quickly and quietly. Physicist John von Neumann first wrote about this in the 1940s. He called them universal constructors, and the idea was more mathematical than mechanical at first. But it stuck. Today, engineers are starting to study how they might be built: tiny robotic arms, automated mining units, and onboard 3D printers that could turn dust and rock into spare parts. These machines don't need to look like ships or probes. They might be small, rugged, and built to blend into the very environment they use for materials. What if these machines are already out there? Space is full of noise. Thousands of known objects move through the inner solar system each year. They're tracked and recorded, some from Earth-based telescopes, others by satellites. Most follow regular paths, but they also vary widely in shape, rotation, size, and brightness. Some tumble, some flare. Some change speed in small, unexplained ways. If one of these were artificial, made of metal and machinery rather than rock, how could we tell? This question has begun to form part of a newer kind of research, the search for lurkers. These are hypothetical devices placed in long, slow orbits, watching planets or collecting data without giving themselves away. Instead of fast-moving probes or active beacons, lurkers would be passive. They'd be quiet and hard to spot, especially if their outer surfaces looked like stone. If the goal is to watch without being seen, hiding as a space rock might be one of the best methods available. A self-replicating asteroid AI wouldn't necessarily shine or send signals. It might be cold and still most of the time. Only when near a source of energy, like the sun, might it wake up and process data. If it's really advanced, it could mine the surface of other asteroids, storing materials inside its body, or using local elements to repair worn parts. It could have sensors buried deep under layers of dust, where cosmic rays and micrometeorites wouldn't damage them. Detecting something like this is extremely hard. Our tools are still built around looking for light, heat, or gas. But a small machine hidden in rock or covered in a thick crust of carbon and metal might not give off any signal at all. Its spectrum could look like a dusty asteroid. Its path might seem natural. Only by catching some irregular motion or behavior would we notice anything strange. Even then, we might not know what we're seeing. One area of interest is thermal analysis. Some space rocks heat and cool in ways that don't quite match their expected material makeup. If an object retains heat longer than it should, or reflects less light than expected, it might have an unusual core. There have already been a few cases where objects turned out to be artificial. Old rocket boosters, for example, that circled back toward Earth decades after launch. But these were identified quickly through their orbits and known histories. Something truly interstellar, with no human origin, would be a different story. Researchers have also considered how self-replicating machines might behave over long timescales. If they exist, they might be extremely old. They might operate at slow speeds, only activating under certain conditions. They might only send a signal once every 1,000 years, or only when approached. In this model, most of the time they are indistinguishable from the natural objects around them. Some thinkers suggest we may need to look at behaviors rather than appearances. Does an object drift slightly off course with no clear source of thrust? Does it maintain a spin rate that seems unnatural? Does it show repeated patterns in brightness that don't match any known rock or metal? These are subtle clues. On their own, they don't prove anything, but taken together, they might point toward a new kind of object. One way this idea could become testable is through future flybys or sample return missions. If a probe were to visit a strange object and drill into it, only to find circuits or advanced alloys, the case would be clear. But this is still far away. Most objects in interstellar space pass through too quickly to catch. Even closer-in rocks take years to reach. For now, we must rely on careful observation and creative thinking. What signs would an artificial object leave behind? What tools do we need to find them? How many of the rocks we ignore are just rocks? And how many are more than that? As we search the skies for clues, these are questions we are only beginning to ask. The answers, if they ever come, may change not just how we see space, but how we understand what might already be in it. Cosmic rays and surface chemistry, alteration over eons. Unlike the inner solar system, where bodies are protected somewhat by the sun's magnetic field and solar wind, deep interstellar space offers no such shield. The journey through the galaxy exposes objects to a constant bombardment of high-energy particles. These cosmic rays are mostly made of protons, but also include electrons and atomic nuclei. They zip through space at nearly the speed of light, coming from exploding stars, black holes, and other extreme events scattered across the galaxy. When cosmic rays hit the surface of an object, they crash into atoms, break chemical bonds, and set off a series of reactions. Over time, this repeated exposure can dramatically alter the chemistry of the surface. Hydrogen can be knocked away. New, more complex molecules can form. Entire compounds can be rearranged. This slow but relentless process is called space weathering. In the lab, scientists have recreated what cosmic ray exposure might do to various ices and rocks. For example, simple molecules like methane or ammonia, when frozen and exposed to radiation, can transform into heavier hydrocarbons or even tar-like organic substances. Over eons, these materials darken and harden. They build up into crusts that are chemically different from the original material below. Some of these surfaces can become almost inert. Scientists have also considered how deep this processed layer might go. For an object spending time in interstellar space, the depth of alteration depends on how long it's been out there and how energetic the radiation is. Estimates suggest that over millions of years, cosmic rays can penetrate several centimeters into the surface, sometimes more. That might not sound like much, but for a small body like Oumuamua, only about 100 meters long, this could represent a large percentage of its outer material. If this layer is dark, rigid and chemically altered, it could strongly affect how the object reflects light, how it warms, and how it behaves when close to a star. This idea of cosmic ray alteration also hints at why we don't often see such features in solar system objects. Many of our comets, for example, are thought to come from the Oort cloud, far beyond Pluto. Even though they've been away from the Sun for billions of years, they are still within the boundary of the solar system. They're bathed in the Sun's weak but ever-present influence. And once they come close to the Sun, their surface material gets blasted away, exposing fresh layers below. As a result, we mostly see the younger material that hasn't been exposed to galactic radiation for nearly as long. Oumuamua, by contrast, may have been travelling without interruption for much longer. Its surface may not have been refreshed in any way. The smooth, reddened coating could represent a record of ancient cosmic processes, etched by particles from distant supernovae or galactic magnetic fields. In this sense, it could act like a time capsule. Though we didn't get to examine it up close, the surface features alone might hold information about the conditions of deep space that we can't study in any other way. There's also the question of whether this radiation-altered material affects the object's motion. Some researchers have speculated that if the surface becomes particularly thin or flaky, solar radiation pressure might be more effective than usual. Light from the Sun, bouncing off a dark, processed crust, could push slightly more than expected, especially if that surface is unusually smooth or low in density. That might help explain, in part, the non-gravitational acceleration. It wasn't just what it was made of, it was what had been done to it by time and space. Another factor in this long exposure is temperature. The average temperature in interstellar space is around negative 270 degrees Celsius, barely above absolute zero. At this temperature, materials behave very differently. Ices become hard as rock, molecules slow to near stillness, and yet the occasional strike by a high-energy particle can still rearrange their structure. The surface may remain stable on the outside, but constantly shift beneath, forming more complex compounds over time. These effects build up slowly, but across the lifespan of an interstellar traveller, they are impossible to ignore. The challenge now is to apply this understanding to other potential visitors. If we see future interstellar objects, and with new telescopes, this is increasingly likely, we might begin to look for the fingerprints of radiation exposure right away. Colour, reflectivity, and even the thermal behaviour of these bodies could all help tell the story of where they've been and how long they've wandered. Oumuamua gave us a glimpse into a different kind of surface, one shaped not by collisions, heat, or volcanic forces, but by quiet, invisible impacts over countless centuries. Galactic radiation, while not violent in the way we think of asteroid strikes or solar flares, may be just as powerful in its slow reshaping of the cosmos. For Oumuamua, this cosmic sandblasting may have left it wrapped in a skin moulded by the galaxy itself. Tumbling through space. Rotation state evolution. Asteroids and comets tend to settle into a stable rotation state over time. After enough collisions or internal movements, they often spin around one axis in a regular and predictable way. Imagine a football thrown in a tight spiral or a planet rotating around its poles. That kind of motion is called principal axis rotation. It's the simplest and most energy-efficient way for a body to rotate, especially if there are no outside forces constantly disturbing it. But not all objects follow that clean rotation. Some, especially those that have experienced sudden impacts or irregular outgassing events, can end up in a non-principal axis rotation. This is more like a chaotic tumble. Instead of spinning around a single axis, the body wobbles through space, its spin shifting in direction and speed over time. It's harder to model, and it doesn't look the same from one day to the next. That's what astronomers saw with Oumuamua. Its tumbling motion is harder to predict, and it often means that the object hasn't been spinning that way forever. Tumbling usually requires some trigger, a force strong enough to knock the object off balance. If Oumuamua was already tumbling when it arrived, the cause must lie much further back in its history. One possibility is that the tumbling was a result of a collision in its original star system, long before it entered ours. A glancing blow from another object could have sent it spinning in an odd way, and without any strong forces to slow it down in deep space, that motion would have continued for millions of years. Some researchers explored whether its odd shape contributed to its rotation. Long or flat bodies are more prone to wobbling, especially if their mass isn't distributed evenly. As they spin, the torque caused by even slight differences in mass or shape can lead to complex motions. The exact ratio between its longest and shortest dimensions is still debated, but many models agree it was at least 5 to 10 times longer than it was wide. The tumbling also tells us something about the object's age and structural strength. In some cases, small bodies eventually settle into a stable spin state, even after being disturbed. This happens through a process called internal energy dissipation. As the object wobbles, internal friction slowly converts rotational energy into heat, calming the spin over time. But this process can take thousands to millions of years, depending on the object's material and size. The fact that Oumuamua was still tumbling when we saw it suggests either the disturbance was recent or the object is rigid enough to resist internal energy loss. Another factor that came under discussion was the Yarkovsky-O'Keefe-Radzievsky-Paddock effect, or the Yorpi effect, a subtle force caused by sunlight hitting the object unevenly. Over long periods, light absorbed and re-emitted by the surface can actually change the spin rate of small bodies. In the case of Oumuamua, its brief time in the solar system wasn't long enough for this to have much effect, but over millions of years in another system, such a force might have gradually altered its rotation. Whether the Yorp effect contributed to the tumbling or not is still uncertain, but it's another reminder of how even small forces can add up over cosmic timescales. Some astronomers hope that careful modelling of the tumbling motion might reveal more about the object's shape or interior. For example, certain spin patterns might only be possible if the object has a hollow section or is made of unusually light material, but the available data was limited. Still, the models created from those observations have given us one of the clearest glimpses into its physical behaviour. One interesting detail from those models is that the tumbling seemed to be fairly slow. It wasn't spinning rapidly like a meteorite burning through Earth's atmosphere. Instead, it took hours for the object to complete even part of a rotation. That slow, irregular spin would also make it hard to generate any steady force from gas jets, further supporting the idea that outgassing, if it occurred at all, was weak and scattered. For now, its tumbling motion remains one of the clearest physical signals it left behind. As with so many features of this object, the spin holds clues. And for astronomers piecing together the story of Oumuamua, even a wobble can tell a story. Peculiar porosity. What's hiding beneath the crust? When scientists talk about porosity in space rocks, they mean how much of the object's volume is empty. In other words, it's the ratio between solid material and the voids or pockets within it. Most asteroids and comets in our solar system have some degree of porosity. Many have been fractured over time, hit by impacts, or broken and reassembled by gravity into what are sometimes called rubble piles. These objects might have porosity in the range of 20 to 50%, meaning half of their internal structure could be empty space. To explain its odd behaviour, some have wondered whether Oumuamua might have an extremely high porosity, perhaps 70, 80, or even 90%. That would mean most of the object isn't solid material at all. It would be like a foam or a lattice, barely holding together, but light and fragile enough to interact differently with the environment around it. The idea of such a porous body helps explain a few puzzles. For one, if it was made of very low-density material, then even a small amount of solar radiation pressure could have a greater effect. It would be like blowing on a balloon compared to blowing on a rock. The lighter the object, the more it moves from even small pushes. Another part of the puzzle is thermal conductivity. Dense, rocky bodies conduct heat well, but a very porous object acts like insulation. Its surface might heat up quickly, but the inside stays cold. If Oumuamua had buried ices, the heat might not have reached them at all, or at least not enough to trigger a strong outgassing response. This could explain why we saw no visible coma, even though something clearly changed the object's path. To explore this further, scientists turned to models of how different materials behave in space. If the body was made of frozen gases, like nitrogen or carbon monoxide, and had a structure filled with microscopic voids, it might match the observed behavior. Some researchers pointed to the idea of a fractal aggregate, a collection of fine particles loosely bound together into a larger whole, but with so much space between the particles that the entire structure is more air than substance. On Earth, we might compare this to a snowflake or a dust bunny, light, fluffy, and fragile. The porosity also has implications for how Oumuamua formed. If it really is a fragile, low-density object, it probably didn't come from a violent origin. A major collision or impact would likely destroy such a structure. Instead, it might have formed gently, in the outer regions of another star system, far from strong gravitational forces. There, fine particles could slowly come together, collecting through electrostatic forces or weak gravity, until a larger body formed. Comparative case, 2I/Borisov's cometary profile. When astronomers detected the object known as 2I/Borisov in August 2019, it marked a turning point. Oumuamua had raised more questions than answers. Now, with Borisov's arrival, scientists had a second chance. This was a rare opportunity to compare two objects born in other star systems. What stood out almost immediately was how different Borisov was from Oumuamua. Gennady Borisov, an amateur astronomer in Crimea, spotted the object using a custom-built telescope. At first, the motion of the object in the sky suggested a typical solar system comet, until orbital calculations showed its path wasn't bound to the Sun. Just like Oumuamua, this object was moving too fast, on a hyperbolic orbit. It had come from beyond the solar system, made its pass through, and would exit back into interstellar space. But unlike Oumuamua, Borisov looked familiar in many ways. Early observations showed a clear coma, the classic sign of a comet. In Borisov's case, the coma appeared quite early, even when the object was still far from the Sun. This told researchers that its surface was rich in volatile materials like carbon monoxide or water ice that could sublimate even in cold temperatures. Borisov's appearance was remarkably normal. It looked like a comet from our own solar system, and that surprised many scientists. After Oumuamua's strange, silent passage, some expected interstellar objects to be equally unusual. Instead, Borisov suggested that some of these travelers might not be so different after all. Borisov's spectrum showed the familiar signs of cyanide gas and diatomic carbon. These are molecules commonly found in active comets. Researchers also measured the object's dust production. They found it was releasing large amounts of fine particles into space, forming a tail that stretched out behind it. The particles were mostly submicron in size, just like those seen in solar system comets. Everything about Borisov pointed to a volatile-rich, dusty body, a normal comet, if one can call anything interstellar normal. The differences between Borisov and Oumuamua became clearer as both were studied in more detail. Borisov had a steady outgassing profile, a roughly spherical shape, and it followed a path through the solar system consistent with the behavior of comets, gradually bending due to gravity, but without unexplained acceleration. With Borisov, astronomers were able to look at the ratios of different gases and compare them to known comets. Some surprises came up. For example, Borisov was unusually rich in carbon monoxide, which suggested it had formed in a very cold region of its home system, possibly farther from its star than where most of our own comets originated. This hinted that even though the object looked familiar, it still carried clues about different formation environments. That kind of data was impossible to get with Oumuamua. Its faintness and lack of activity made it hard to study in detail. But Borisov was different. It was bright, active and visible for many months. Large telescopes from around the world turned their attention to it. Hubble captured high-resolution images of the coma and tail. The Atacama Large Millimeter Array in Chile detected gas emissions at different wavelengths. The European Southern Observatories VLT took spectra from the dust. All these observations added to a growing picture. Borisov was acting like a classic comet that just happened to come from another star. Why were these two interstellar objects so different? Was Oumuamua the odd one, or was Borisov just the first of many more normal-looking visitors? One idea is that there are many types of material that can be ejected from forming star systems. Some fragments, like Borisov, might come from the icy outer zones and retain a lot of volatile compounds. Others, like Oumuamua, could come from drier, inner regions, or might have been altered by long journeys through space. The amount of time these objects spend drifting between stars could also matter. Cosmic rays, micrometeorite impacts, and thermal cycling might erode or change a body over millions of years. Oumuamua may have been weathered into something unrecognizable. There's also the possibility that the differences reflect their size. Borisov was estimated to be much larger, perhaps hundreds of meters in diameter, while Oumuamua might have been as small as 100 meters or less. Smaller objects can be more affected by radiation pressure, thermal changes, and material loss. A thin crust or unusual shape could develop over time. Some scientists wonder if Borisov, too, might eventually resemble Oumuamua after eons in interstellar space. Still, the contrast remains striking. Borisov showed that it is possible for interstellar comets to resemble those we know well. That helps validate existing models of how planetary systems form and evolve. It also makes future discoveries easier to interpret. If another comet-like object enters the solar system, scientists now have a clearer idea of what to look for and how to study it. On the other hand, Oumuamua's mystery deepens by comparison. It may be unique, or it may represent a class of objects we have yet to fully recognize. Because Borisov was caught while still far from the Sun, it could be tracked and studied over a longer period. Observations were planned well in advance. Telescopes coordinated data collection. Researchers built models in real time. Borisov's case helped strengthen the argument for expanded sky surveys and better preparedness for interstellar discoveries. More objects like Borisov are likely to come. As new data is collected, astronomers hope to build a catalogue of these objects. Whether they look like Borisov or like Oumuamua, they help us understand how planets form, how solar systems scatter their leftovers, and how those pieces drift through the galaxy. Meteoric Intruder, the CNEOS 2014-1-8 Fireball. In the quiet hours of January 8, 2014, something entered Earth's atmosphere over the South Pacific near Papua New Guinea. It was unusually fast and burned bright as it streaked across the sky. Most people never heard about it at the time. It wasn't spotted by any telescope or part of a major astronomical survey. Instead, the object revealed itself through pressure waves, recorded by infrasound sensors positioned around the globe. These are the same types of instruments used to detect nuclear explosions and other powerful atmospheric events. But this event wasn't man-made. It was natural. It was a meteor, and not just any meteor. It was something that would, years later, be flagged as potentially the first known interstellar object to hit Earth. The object, later catalogued as CNEOS 2014-1-8, was recorded by the US Department of Defense's sensors, part of the worldwide monitoring network used for compliance with nuclear test bans. When a high-energy fireball occurs in the atmosphere, it produces low-frequency sound waves that travel for hundreds or thousands of kilometers. These waves are silent to human ears but can be picked up by the specialized instruments. The data included the fireball's speed, altitude of explosion, and rough location. Nothing about this seemed strange at first glance. Earth is hit by dozens of small meteoroids every day. Most burn up before reaching the surface. This one appeared to be another routine entry. But the data told a different story when researchers analysed it closely. The object entered the atmosphere at an extremely high speed, around 45 kilometers per second relative to Earth. What made this figure stand out was not just the number itself, but what it meant. Once Earth's own motion around the Sun was subtracted from the calculation, the object's velocity relative to the Sun still exceeded the escape velocity of the solar system. In other words, even before it hit our atmosphere, this object was already moving fast enough to break free of the Sun's gravity. That's a defining feature of an interstellar origin. It meant this object had travelled across interstellar space before slamming into Earth. The recognition didn't happen right away. The original event in 2014 was stored in the public Fireball database maintained by the Center for Near-Earth Object Studies, or CNEOS, which compiles impact events recorded by US government sensors. It wasn't until 2019 that two researchers, Amir Siraj and Avi Loeb at Harvard University, dug into the database and noticed something unusual. They were looking for high-speed events, ones that hinted at interstellar origin. The January 2014 fireball stood out. The data suggested it had a hyperbolic trajectory. They ran the numbers and concluded that the odds it was from beyond the solar system were very high. They wrote a paper on their findings and submitted it for peer review. But there was a problem. The data they used came from military sensors, and parts of it were considered classified. That meant independent scientists couldn't confirm their analysis. Without full access to the precision measurements, journals were reluctant to publish. The discovery sat in limbo. It wasn't until April 2022 that the US Space Command officially confirmed that the velocity estimate was accurate. In a memo, they stated with 99.999% confidence that the object was interstellar. This simple acknowledgement validated the earlier claims. CNEOS 2014-1-8, also known as Interstellar Meteor 1, or IM1, had entered Earth's atmosphere at interstellar speed. It was, very likely, a visitor from another star that didn't just pass by, but made contact. Unlike Oumuamua or Borisov, IM1 was small, probably less than a meter in diameter. It didn't survive its fiery descent. It exploded in the atmosphere and scattered into the ocean. But its journey, its origin, and the way it was detected all made it unique. It didn't show up in a telescope. It didn't reflect sunlight or display a trail across the sky that astronomers could track. It was detected through its physical impact, through the shock waves it left in the air. This makes it a fundamentally different type of interstellar detection, a bottom-up discovery, where the object reveals itself through destruction rather than reflection. The fireball's trajectory could also be reconstructed to some extent using triangulation from multiple infrasound stations and satellite data. The path it took through the atmosphere suggested a steep, almost direct entry angle. It came in fast and didn't slow down much until it hit the thicker parts of the atmosphere. There was no visible coma, no tail, and no time for detailed study. It arrived unannounced and vanished in seconds. Objects like IM1 are too small and too fast for telescopes like Pan-STARRS and Catalina. They don't reflect enough light to be spotted in advance. They go unnoticed until they enter the atmosphere and explode. What was Oumuamua made of? Did it resemble meteorites that we find on Earth? Was its material altered by millions of years in deep space? Could we recover pieces of it from the ocean floor? A 2023 expedition funded by Avi Loeb and others set out to recover possible fragments of the object from the seabed near the impact site, using a magnetic sled to collect tiny spherules from the ocean floor. The team brought back samples to analyze. The results are still under examination. If any of the recovered material shows isotopic ratios or mineral structures not found in Earth origin objects or typical solar system meteorites, it could be direct evidence of interstellar material. Oumuamua slipped through quietly. Borisov gave us a long show, and Oumuamua gave a brief flash of light and a burst of infrasound. These events are rare, but are starting to form a pattern. They tell us that the solar system is not as isolated as once thought. Interstellar debris doesn't just pass by, it sometimes comes crashing in. The case of the 2014 fireball also underscores how important it is to use all available tools to study the cosmos. Optical telescopes are essential for long-distance surveys, but they have limits. Radar, infrasound, seismic sensors, and even satellite-based detectors offer a different view. They can catch fast or small objects that slip past traditional methods. The combination of detection systems, optical and acoustic, ground-based and orbital, may be the only way to fully catalogue the population of interstellar debris that moves through our neighbourhood. Population statistics. How many Oumuamuas are out there? Oumuamua was only detected because pan-stars happened to be scanning the right area of sky at the right time. That made astronomers realise that for every one interstellar object like Oumuamua, we do see many more must go unnoticed. This is known in astronomy as detection bias. What you detect is shaped by what your instruments are capable of seeing. So researchers began to work backwards. They asked if our surveys are only sensitive to objects of a certain brightness and size, and if we happen to detect one such object in a given time span, what must the actual population be to make that detection likely? These estimates involve some math and modelling, but the idea is simple. If you catch one fish in a very small net, and you know how much ocean you've sampled, you can guess how many fish must be swimming out there in total. The first estimate, published shortly after Oumuamua's discovery, was staggering. It suggested that for one object like Oumuamua to pass through the inner solar system every few years and be caught just once, we must be surrounded by vast numbers of similar objects. One early estimate put the density at roughly 1 per every 100 cubic astronomical units. That might not sound like a lot, but when you scale that across the vast volume of space, it adds up to perhaps a quadrillion interstellar objects like Oumuamua floating through the galaxy. That's a 1 followed by 15 zeros. These aren't objects stuck in orbit around stars. They're between stars, free-floating, kicked out of their home systems by gravitational interactions, planetary migrations, or the death throes of their stars. Some may be icy, others may be rocky or metallic, and most of them are likely invisible to us, either too dark, too small, or passing by at angles that keep them out of view. For decades, astronomers have catalogued the comets and asteroids orbiting our Sun. These include well-known groups like the Asteroid Belt, the Kuiper Belt, and the Oort cloud. Each group has its own characteristics, average sizes, orbits, and frequencies of appearance in the inner solar system. And these populations can be studied in detail. We've sent spacecraft to visit them, photographed them up close, and even brought back samples. But interstellar objects? That's a different game. We've only caught 2 in real time, Oumuamua and Borisov. That's not a large sample, and yet both were found within just a couple of years of each other. When something extremely rare suddenly happens twice, it's often a sign that the phenomenon is more common than first believed. It's not that the universe changed, it's that our tools got better. Models built using the data from Oumuamua and Borisov have tried to answer not just how many such objects exist, but where they might come from. Some may be former planetesimals, small building blocks of planets. Others may be the debris of collisions or stellar events. Still others might have once orbited rogue planets, planets that themselves drift between stars. Not all interstellar objects travel at the same speed. Some are slow, just barely exceeding solar escape velocity. Others, like IM-1, come in fast, possibly due to being flung out of massive systems or accelerated by gravitational encounters. This affects their likelihood of being captured by gravity or slowed down enough to pass near Earth. And if they're moving too fast, our current survey techniques may miss them completely. Some researchers have also looked at whether any of these objects might actually become temporary members of our solar system. If an interstellar object passes close enough to a planet, it might be captured briefly, orbit for a while, and then escape again. This idea opens the door to the possibility that some objects currently orbiting the Sun could have originated elsewhere, and we just don't know it. Their orbits might look natural, but their composition might tell another story. And there's the big question: are we seeing the full range of what's out there? If Oumuamua was unusually elongated or light, it might have been easier to detect. But what if most interstellar objects are even smaller, or darker, or follow weirder paths? That would mean our current detections are biased toward just a narrow slice of the population. What we've seen might not be the most common kind, just the easiest to spot. All of this means that the galaxy is likely filled with relics, leftovers from long-gone solar systems, or fragments of worlds never formed. They drift, waiting for chance alignments that bring them into view for a moment before they vanish again into the dark. And while most of them are harmless, the idea that Earth is not just surrounded by, but occasionally struck by interstellar objects, is a new chapter in our understanding of cosmic traffic. Detection biases, the blind spots of current surveys. Some things in the sky are simply harder to find than others. That's a fact astronomers have always had to deal with. Telescopes don't see everything. They see what they're designed to detect. But there's always a trade-off: field of view versus detail, brightness versus motion, fast versus slow. With interstellar objects, the problem becomes even more tricky, since these visitors might not behave the way familiar solar system objects do. Take Pan-STARRS, for example. It's one of the best wide-field survey telescopes ever built. It's particularly good at catching near-Earth asteroids and other small bodies that reflect enough light to show up clearly. But even Pan-STARRS has limits. Its sensitivity drops off for objects that are small, fast, dark, or approaching from difficult angles. One big blind spot is speed. Oumuamua was fast, but not too fast. It was moving at about 26 kilometers per second relative to the Sun. Faster than solar system asteroids, but still slow enough to show up in multiple images as a clear moving object. But what about faster interstellar objects? Ones moving at 50 or 60 kilometers per second, or even more. Those can slip by in a flash, literally. They may only be visible in 1 or 2 frames, not enough for tracking software to lock on. And if their brightness is already low, they might just look like a cosmic ray hit or a smudge on the sensor. Most Earth-crossing asteroids approach the planet from along the plane of the solar system, so that's where our surveys are focused. But interstellar objects can come from any angle, above, below, or from the sides of the solar system. If they approach from directions where our surveys are less focused, especially near the Sun in the sky, we might miss them entirely. Low approach angles are a particular problem. If an object is coming almost straight toward us, its motion across the sky, its apparent motion, is very slow. It won't streak like a typical asteroid. It may appear as a nearly stationary point of light, and that confuses detection algorithms. Our software is designed to flag motion, and it often filters out objects that aren't moving enough. Ironically, a very fast object on a collision course might seem stationary because of the way perspective compresses its path into a single dot. By the time it's close enough to reveal its speed, it may already be too late to see. Size and brightness are tied together as well. A larger object reflects more sunlight and is easier to detect. Had Oumuamua been half the size, Pan-STARRS might not have seen it. If it had been darker, it might have stayed invisible. Our surveys are tuned to catch things above a certain brightness threshold. Anything dimmer gets lost in the noise. Then there's the question of how often we look. Pan-STARRS covers large areas of sky, but not all of it at once. It scans specific regions each night, then moves on. That means objects can pass through its field of view between scans, never appearing in any frame. There are gaps in time and gaps in coverage. Another issue comes from the software itself. Detection pipelines are built to catch known types of objects. They flag fast-moving dots, streaks, and changing positions. But they're trained on Earth-crossing asteroids and solar system comets. When something strange shows up, it may be flagged as an anomaly and discarded automatically. Human review helps catch some of these cases, but with millions of images being taken, it's impossible to eyeball every single one. Many potential detections are likely buried in old data, never having triggered the right threshold. Some researchers have tried to go back into archival data to look for missed interstellar objects. It's slow work. It means combing through years of telescope frames, checking for faint moving dots that were overlooked. A few candidates have been proposed, but none confirmed. This highlights how much we may be missing, not because the objects aren't there, but because our tools weren't tuned to find them at the time. Contrast this with how we find typical Earth-threatening asteroids. These are usually larger, slower, and spend more time in the inner solar system. They return on predictable orbits. We can track them, catalogue them, and plan follow-up observations. Some new strategies are being proposed to deal with these blind spots. One idea is to develop faster image processing algorithms that can catch high-speed objects before they vanish. Another is to build space-based telescopes that don't suffer from Earth's day-night cycle or weather. By stationing a survey telescope at a solar orbit near Earth, it could watch the skies continuously and catch objects approaching from sunward directions, an area almost completely blind to ground-based telescopes. There's also growing interest in using infrared detection. Many small objects, even if dark in visible light, still emit infrared radiation from the warmth of sunlight. An object that's too dim to see in an optical image might glow faintly in thermal wavelengths. Infrared space telescopes like NEOWISE have demonstrated this capability, and future missions like the NEO Surveyor, due to be launched in 2027, could expand it. But no system is perfect. The sky is too big, the objects too small and fast. There will always be some we miss. What scientists try to do instead is understand the scale of the problem and what we can infer from the few we do detect. Every new detection gives us more data to refine our models. Over time, that helps improve the odds of spotting the next one. In the end, detection bias isn't a flaw, it's a known limitation. It tells us where to look harder, what to improve, and how to recalibrate our expectations. NextGen observatories, Vera C. Rubin and the LSS T-ERA. Sitting high in the Chilean Andes, the Vera C. Rubin Observatory is poised to transform how we observe the sky when it comes online in late 2025. The key to its power is the LSST, the Legacy Survey of Space and Time. While the name might sound formal, its goal is straightforward: take the widest, deepest, and most frequent pictures of the night sky ever attempted. Over 10 years, LSST will produce a detailed, constantly updated map of the visible universe. That includes the faintest galaxies, exploding stars, drifting asteroids, and if they're out there, more interstellar objects like Oumuamua. At the heart of the Rubin Observatory is a massive 8.4-metre telescope. It will use a single, enormous camera, the largest digital camera ever built for astronomy. With a resolution of 3.2 billion pixels, each image it captures will cover a huge chunk of the sky. And it won't just take a few snapshots each night. LSST will scan the entire visible sky every few nights, again and again, for years. This regular pattern of observations is exactly what's needed to detect fast-moving, one-time visitors from beyond the solar system. One of the biggest advantages LSST brings is its ability to spot dim, fast-moving objects before they pass us. LSST's sensitivity will allow it to see faint objects like Oumuamua earlier when they're still approaching and when they reflect more sunlight. That early detection means more time to observe, more time to study, and a better chance of figuring out what kind of object we're looking at. LSST's wide field of view means it can watch much more of the sky at once. Many current surveys only scan narrow strips of sky each night. Objects that pass outside those strips aren't seen. LSST, in contrast, will image roughly 20,000 square degrees, the vast majority of the entire sky visible from Earth, on a regular loop. That nearly full sky coverage reduces the chance of missing interstellar objects that come in at strange angles or speeds. No longer will they need to appear in just the right place, at just the right time to be noticed. And while ground-based telescopes can't see objects coming directly from the direction of the Sun, LSST's speed of scanning improves the odds of catching objects as they arc away from that region. In the days after they round the Sun, when they're still bright and close, LSST might detect what older surveys would have missed entirely. Another major improvement LSST offers is its cadence, how often it revisits the same part of the sky. Many telescopes only look at a specific region every few days or weeks. That leaves big gaps in coverage. LSST will revisit the same patches of sky every few nights. That rapid repetition helps catch fast-moving objects that might otherwise appear in only 1 or 2 frames before vanishing. With more data points over shorter time spans, it's easier to spot the subtle movements that signal something interesting. Once those movements are flagged, LSST's processing system kicks in. It's designed to issue alerts in near real time, within 60 seconds of detecting a change, whether it's a new object, a moving one, or a brightening one. The system will send out an alert to astronomers worldwide. That's critical for interstellar objects. Since they don't come back, every hour counts. A quick alert means other telescopes, including those in space, can swing into position for follow-up observations. Together, they can capture colour, spectrum, shape, and maybe even gases or dust. The software behind LSST is built to be smart. Using machine learning and advanced algorithms, it will sift through millions of observations every night. It has to. LSST will generate up to 20 terabytes of data per night. That's more than any previous survey telescope has ever produced. The system is designed not just to handle the data, but to recognize patterns in it, spotting outliers that might be missed by traditional filters. This opens the door to finding not just more interstellar visitors, but new types of them. Maybe objects like Oumuamua are rare, and most interstellar bodies look more like Borisov. Or maybe we've just scratched the surface, and there's a wide range of shapes, compositions, and behaviours waiting to be found. With its speed, depth, and coverage, LSST can help answer that. But even with LSST, challenges remain. One is the need for coordinated follow-up. LSST will detect potential interstellar candidates, but confirming them requires precise tracking and additional data. That means global cooperation, telescopes across different time zones, wavelengths, and observing conditions. When LSST finds something interesting, the scientific world will have to move quickly, coordinating observations to learn as much as possible before the object fades or flies away. There's a chance that LSST will find objects that don't fit into any known category, strange movers, flashes that don't repeat, faint, fast dots that brighten without explanation. LSST is not just a discovery machine. It's an opportunity to uncover the unknown. When data is collected at this scale and speed, surprises are guaranteed. In the longer run, LSST might do more than just discover more interstellar objects. It could help reveal where they come from. With enough detections, scientists can study their paths backward. That data might show whether most visitors are coming from certain parts of the galaxy, or whether they're truly random. That kind of mapping could hint at other planetary systems ejecting debris, or even more exotic origins. In that sense, LSST is more than a telescope. It's a time machine and a map. By giving us better eyes, it gives us a better chance to understand what's really moving through the solar system. Synthetic tracking, boosting small body discovery rates. Synthetic tracking is a method that allows scientists to find fast transients by working around the blur problem. Traditional surveys use a fixed exposure image. A telescope takes a picture of the sky, and if something in it moves too much during that exposure, it creates a streak. Or worse, it dims out and becomes undetectable. But with synthetic tracking, instead of taking one long image, telescopes take a rapid series of short exposures. Each image captures the sky with only a short window of movement. Individually, the object may not be visible, but when the images are combined in a specific way, shifted along the predicted path of the moving object, and then stacked, the object reappears. The noise stays random and averages out, but the object being tracked adds up and becomes brighter. It's like trying to spot a firefly in a dark forest. If you stare in one place, you might never see it, but if you know where it's going and follow that path with your eyes, it starts to stand out. Synthetic tracking does the same thing, but with math and pixels. This method is especially powerful for detecting objects that are both small and moving quickly. Synthetic tracking allows astronomers to simulate different motion patterns and effectively reconstruct the object's path from fragments hidden across a time sequence of images. The process begins with a burst of images taken over a short period, sometimes 30 to 60 frames in under an hour. Software then shifts these images according to a trial velocity vector, essentially guessing how fast and in what direction the object might be moving. This trial shift is repeated across thousands of different possible paths. For each combination, the software stacks the frames and checks to see if a signal emerges. It's a data-heavy process. The software must scan through an enormous number of motion combinations to find a real one. But when a match is found, a faint moving dot appears where there was once only static. The number of possible motion paths grows quickly. At high speeds or long observation windows, the object may move across multiple parts of the image frame. Tracking must adjust for distortions, rotation, and sometimes even field curvature. But with advances in computing power and more efficient algorithms, synthetic tracking has become increasingly practical, even for ground-based observatories. One group pioneering this approach is the B612 Foundation, a non-profit focused on planetary defense. Their research uses synthetic tracking to search for near-Earth objects too small and fast to be detected through normal survey methods. Using telescopes like the 0.7-metre Baker-Nunn camera, they've demonstrated that it's possible to spot metre-sized asteroids that would otherwise go unnoticed. They've successfully tracked objects on Earth-crossing paths using equipment that's not at the cutting edge of aperture size or sensitivity. In orbit above Earth's atmosphere, instruments benefit from clearer skies and less distortion. But even with this advantage, faint objects still need synthetic tracking to rise above the noise floor. With less light pollution and no weather interference, space observatories can collect more reliable image sequences. Combine that with synthetic tracking, and even smaller, dimmer objects can be revealed. Missions under development, like NASA's Near-Earth Object Surveyor, are exploring ways to incorporate these techniques to increase their discovery potential. Synthetic tracking removes certain detection biases by opening up the detection space. And it's not just about discovery. Once an object is detected, synthetic tracking data can help improve its orbital solution. With a precise record of movement across many short exposures, scientists can backtrack and forecast its path with greater accuracy. That, in turn, allows for better planning of follow-up observations and even mission proposals. In the future, if synthetic tracking helps identify an interstellar object early enough, it might give scientists time to launch a probe, something that wasn't possible for Oumuamua. There's also room for combining synthetic tracking with machine learning. As datasets grow and as more synthetic track detections are confirmed, neural networks can be trained to recognize likely motion patterns faster. This would reduce the number of trial vectors required and shorten the search time for faint movers. Some teams are already testing early versions of such systems, hoping to make synthetic tracking not only accurate, but also fast enough for real-time surveys. Historical survey archives made up of raw time-sequenced images may contain countless hidden gems. With no streaks or bright flashes to mark them, they were invisible at the time. But by applying synthetic tracking techniques to these archives, it's possible to uncover new discoveries in old frames, objects that have long since left the inner solar system, but whose brief appearances were quietly recorded. Synthetic tracking expands the window of visibility. It gives astronomers a longer time to catch fast visitors and a greater chance to notice them before they're gone. Combined with next-generation telescopes, it becomes a powerful complement, bridging gaps in speed, brightness, and direction that have limited discoveries in the past. The search for fast-moving interstellar objects is a test of how well we can read a sky that's constantly in motion. With tools like synthetic tracking, astronomers are learning to see the invisible, not by building bigger mirrors, but by thinking differently about how to assemble the puzzle pieces of light and motion. And as they do, the picture of our cosmic neighborhood becomes clearer. Machine learning for interstellar alerts. In the early days of sky monitoring, discovery meant human eyes combing through photographic plates. Later came automated systems designed to detect changes or motion by comparing frames over time. These systems used rules, thresholds for brightness, limits for motion, flags for shape. They worked well for known kinds of objects. But as sky surveys became deeper and faster, the rules began to show their limits. They were not flexible enough to adapt to outliers. Machine learning has stepped in to fill that gap. Instead of relying on fixed thresholds, these systems learn patterns from real data. An algorithm doesn't need to be told what to look for in rigid terms. It can study thousands or millions of examples and begin to recognize what is typical and what might be something entirely different. That's a major shift in how discoveries are made. It moves from reacting to the known to anticipating the unknown. To train a machine learning system to detect potential interstellar objects, scientists first have to build a data set. This includes known objects, asteroids, comets, satellites, and the occasional telescope artifact, as well as simulated data of what an interstellar object might look like. These simulations include hyperbolic orbits, high inbound velocities, steep approach angles, and short visibility windows. The algorithm is then trained to pick up on these features in a sea of ordinary detections. It learns to recognize tracks that curve outward instead of closing in. It notices when something moves across the sky faster than it should, or appears only briefly in a location where no object was expected. The result is a classifier, an AI that can look at new data and sort it with remarkable precision. It doesn't get tired or bored. It doesn't ignore strange results because they seem too strange. If trained well, it flags anything unusual, including those few rare candidates that could be the next Oumuamua. One example of this approach in action is found in the work of researchers using data from the Zwicky Transient Facility. Their neural networks are designed to scan transient detections and classify them not just by brightness or motion, but by orbital elements and kinematic clues. A key feature in these systems is the ability to evaluate how likely an orbit is to be hyperbolic. That involves comparing motion over a sequence of images, estimating a preliminary path, and calculating whether it closes around the Sun or flies past it forever. As previously mentioned, most asteroids have orbital eccentricities between 0 and 1, while a hyperbolic orbit has an eccentricity greater than 1. The AI can be trained to recognize these patterns faster and with greater sensitivity than a traditional pipeline. It doesn't have to wait for a human to review or for the full orbit to be calculated. It can issue an alert early, sometimes even before follow-up telescopes are aware of the object. One strength of machine learning is its ability to manage noisy data. AI can recognize faint, fast tracks that match a known pattern, even if the data is messy. It can work across multiple wavelengths and adapt to the quirks of each telescope. And as it continues to learn, it can improve with each new confirmed detection. Scale is another advantage. With future observatories producing multiple terabytes of data per night, no human team could possibly check every candidate. Machine learning offers a way to triage detections. It can assign a confidence score to each object and prioritize those most likely to be unusual. That means astronomers can direct their attention and follow up resources more efficiently. If a fast-moving point of light appears on a hyperbolic path and the AI flags it with a high interstellar probability, that object can be targeted immediately for further observation. The system is also adaptable. If an object turns out to be a false positive, a satellite or piece of space debris, the AI can learn from that mistake and refine its model. Conversely, if it catches something genuinely new, that information feeds back into the training data, making the system more accurate for future detections. This feedback loop is what gives machine learning its edge. It's not just a filter, it evolves. There are also hybrid approaches where AI works alongside more traditional orbital mechanics. Some teams use machine learning to narrow down candidates and then apply high-precision orbit fitting to confirm whether the motion is truly unbound. Others use clustering algorithms to identify groups of anomalies. In one particularly forward-looking project, researchers are exploring generative models. These are algorithms that don't just classify data, but can simulate new data themselves. By generating mock interstellar objects and injecting them into real survey images, they can test how well different detection strategies perform. This process helps tune both the machine learning systems and the survey pipelines that feed them. Real-world alerts have already been issued by machine learning systems. In 2022, a fast-moving object triggered an alert through a neural network pipeline and was flagged for immediate observation. It turned out to be a known asteroid, but the system had correctly picked up on its unusual motion. That kind of near-miss is valuable. It proves that the method works, and that the next time it could catch something truly novel. Machine learning also opens the door to detecting interstellar meteors. Their hypervelocity paths can be reconstructed from infrasound sensors or satellite data. But interpreting that data is difficult. The signals are faint and trajectories can be noisy. AI models trained on fireball data can help identify candidates that arrived at speeds too high for solar system origin. The next frontier may involve combining machine learning with crowdsourced networks. Amateur astronomers and small observatories contribute thousands of images to open databases. AI could scan these decentralized resources in search of patterns that would otherwise go unnoticed. That kind of distributed skywatching, powered by smart algorithms, could vastly increase the odds of catching the next interstellar visitor early. Radiant relics. The case for ancient alien artifacts. adrift in space. Across Earth, traces of long-gone human cultures lie buried under sand, stone and soil. Pottery shards, metal tools, temple foundations. They tell the story of lives lived and lost. In space, there is no soil to bury artifacts, no weather to erode them, and no roots to break them apart. The vacuum offers something Earth does not, near-perfect preservation. Without oxygen, rain, or biology, even fragile things could last millions or even billions of years if built to endure. What if some of the objects we detect from beyond the solar system are remnants? Debris from civilizations that reached the stars long before us and are now silent. Suppose, somewhere in the galaxy, a civilization mastered interstellar travel, or at least managed to launch objects into space on long drifting journeys. Over time, maybe millions of years, those objects would scatter across the stars. It might be wreckage from massive engineering projects, or it might just be waste. Just as human activity on Earth leaves behind landfills and discarded machines, a technological civilization might also have junk. Some of that junk could escape into interstellar space. Bits of failed spacecraft, abandoned modules, or raw materials flung out by mining operations. With enough time, they'd look like space rocks, cold, inactive, and unrecognizable. Their surfaces would be scarred by micrometeorites and cosmic radiation. Their metals would have oxidized if not protected. If once they had lights or circuits, those systems would now be silent. Only their shapes, materials, or patterns might hint at artificial origin. Some scientists have explored this through simulation. How long would it take for a manufactured object, like a probe or a satellite, to lose all obvious signs of its origin? What size would it need to be to survive a billion-year journey through space? Would its orbit ever cross into a planetary system like ours? And if so, would we even recognize it? This challenge lies at the core of space archaeology, a hypothetical field that would treat space as a landscape of lost tools, not just rocks and gas. The rules would be different. There's no digging, no layers of sediment, everything is exposed. But the clues could still be there, ratios of elements not seen in nature, precise geometries that don't form by chance, or isotopes arranged in ways that suggest nuclear processing. For this reason, researchers are increasingly interested in using radar, spectroscopy, and polarimetry to study interstellar objects as soon as they're detected. By analysing how light reflects off the surface, we can get clues about its shape, texture, and possibly its internal structure. If something reflects light like polished metal or exhibits an extremely flat profile, that would be unusual. Not proof of artificial origin, but certainly worth a second look. This idea connects to a much broader question about the Fermi paradox. Why, if the universe is full of planets and possibly life, don't we see signs of intelligence? One possible answer is that we are not looking in the right way. Instead of expecting signals or massive structures, maybe we should be searching for silent relics, like a forgotten tool left on the floor of a darkened room. Some thinkers have proposed launching missions to intercept interstellar objects that pass through our solar system. These missions would aim to photograph, scan, or even retrieve material for study. The biggest hurdle is time. It takes fast decisions and faster spacecraft to catch up, but efforts are being made to develop these kinds of responsive systems. In the future, we may build satellites that wait in deep space, silent watchers that can change course quickly when something strange is spotted. These would be our first archaeological tools in space, not shovels and brushes, but sensors and collectors. The key to all of this is keeping an open mind. The chances that any given object is artificial are very low, but across the galaxy, over billions of years, the possibility exists. And because it only takes one object, one artifact, one piece of a machine to change our understanding forever, the search continues. Astrobiological prospects. Panspermia on interstellar messengers. Panspermia suggests that life might not have started independently in every corner of the universe, but instead spread from one place to another, carried on rocks, dust, or ice. The basic idea isn't that life would have to start during the journey. It's that life, once formed, might be hardy enough to survive the extreme cold, radiation, and vacuum of space, long enough to arrive at a new place where it could take root again. Microbes, particularly bacterial spores, are among the hardiest life forms known. Some can go dormant for thousands or millions of years, sealing themselves in protective shells that resist drying out, freezing, and even moderate radiation. On Earth, we've found these types of organisms in the harshest places imaginable, inside rocks in Antarctica, deep beneath the seafloor, and even in the dry valleys that mimic Martian landscapes. In labs, we've tested them under simulated space conditions. Some bacteria survive long exposure to UV radiation. Others have withstood the vacuum of space for short periods when exposed on the exterior of spacecraft, like the International Space Station. If shielded inside rock, even a thin crust could be enough to protect microbes from the worst of space. But travelling between stars adds a whole new layer of difficulty. The distances are enormous, and so are the timescales. An object like Oumuamua likely travelled for millions, possibly even hundreds of millions of years before it reached our solar system. Over that time, it would have encountered constant bombardment from cosmic rays, which can damage DNA and break down cells. Even the cold of deep space can be challenging. Temperatures just a few degrees above absolute zero cause ice to contract and crack, and organic molecules slowly degrade over time. Still, survival might not be impossible. Some estimates suggest that a microbe embedded even just a few centimeters beneath the surface of a rock could be protected from cosmic rays enough to remain viable for tens of millions of years. Deeper inside, the shielding improves. If such a rock were ejected from a planet or moon with microbial life, perhaps by an asteroid impact, and flung into space, it could begin its journey across the galaxy. If this happened often enough, and over billions of years, then the galaxy could act as a slow circulatory system for life. Instead of life being a rare, isolated event, it might spread gradually, hopping from system to system, starting again when the conditions are right. Oumuamua and Borisov provide a test case. If either object carried embedded ice, rock or dust from its home system, and if those materials had once been part of a habitable environment, then in theory they could contain the frozen remains of life. Not active organisms, but spores, fragments of DNA, or even fossilized structures left behind by simple cells. Whether these could survive depends heavily on the structure of the object. From Earth, we can't easily examine these objects for life or conduct detailed chemical studies. Our best hope might be to send a spacecraft to intercept it. Some mission concepts, like the Project Lyra study, have explored using advanced propulsion to catch up to interstellar objects. A sample return would be a revolution in astrobiology. Inside even a small piece of an interstellar rock, we could search for organic molecules, isotopic signatures, or even microfossils that don't match anything from Earth. Even a trace of strange chemistry, complex carbon chains not made in known processes, would raise big questions. If life is discovered on such an object, or even if strong biosignatures are found, the implications stretch far beyond biology. It would mean that life does not need to form from scratch in every system. Instead, it could mean that the seeds of life are moving through the galaxy all the time, landing on planets and waiting for the right conditions to grow. Earth, in that view, is just one fertile spot where such a seed happened to thrive. This version of panspermia doesn't require intelligent beings. It only asks that life, once it forms, can hang on for long periods in a dormant state. And as more interstellar objects are discovered, we will learn just how common such journeys might be. There's also the reverse possibility to consider. Just as interstellar objects might bring life here, our own material could be escaping into deep space. Impact events on Earth have been known to eject rocks into orbit. Some of these eventually fall back. Others may drift for millions of years. A few could escape the Sun entirely and enter interstellar space. If any carry microbes from Earth, then our planet itself could be a source of panspermia, spreading life to unknown destinations far beyond our reach. Future missions could be designed with this idea in mind. Not only would they intercept and analyze, but they might also drill beneath the surface, scoop out pristine samples from within, and study them in sealed, sterile conditions. A mission of opportunity, intercepting an Oort cloud comet. Unlike the fleeting, high-speed encounters with interstellar visitors, long-period comets entering the inner solar system from the Oort cloud offer a different kind of opportunity. These ancient wanderers, which may have spent billions of years drifting in the outer reaches of our solar neighbourhood, can give scientists a rare look into materials that have been largely untouched since the early days of planetary formation. Even more compelling, their slower approach speeds and more predictable orbits make them easier to intercept with spacecraft, offering a chance to test out the kinds of missions that might one day be aimed at true interstellar objects. The Oort cloud is believed to be a vast spherical shell of icy bodies that surrounds our solar system at distances up to 100,000 astronomical units. These objects are thought to be remnants from the formation of the solar system, flung outward by the gravitational influence of the giant planets long ago. Most of them remain in a distant freeze, too far to see or study, but now and then one gets nudged inward by the passing tug of a nearby star or the gentle pull of galactic tides, and starts a long, slow fall toward the Sun. When one of these long-period comets makes its inward journey, it can take thousands or even millions of years to reach the inner solar system. As it approaches, it often begins to show signs of activity, jets of gas and dust released from ices buried deep inside. These emissions allow astronomers to identify the object, track it, and learn about its composition even before it gets close. Unlike interstellar objects, which can enter suddenly and without warning, long-period comets give us more time to plan and prepare. That extra time is a key reason scientists are looking at these comets as a possible dry run for future interstellar interception missions. Launching a spacecraft to catch up with a visitor from beyond the stars is one of the hardest technical challenges imaginable. The object may be moving at tens of kilometers per second, giving Earth-bound missions just days or weeks to react. But a long-period comet, while still fast, follows a more predictable path and gives months or even years of lead time before closest approach. A spacecraft could be designed in advance, kept in a ready state, or even placed in space ahead of time in a waiting orbit. Then, when a suitable comet is spotted, the mission could be activated, its course set to intercept the inbound object as it enters the inner solar system. If successful, such a mission could approach, orbit, or even land on the comet, depending on the available technology and mission goals. There's already precedent for this kind of work. ESA's Rosetta mission to comet 67P Churyumov-Gerasimenko showed what's possible with careful planning and years of commitment. Rosetta launched in 2004 and arrived at its target in 2014 after a complex series of gravity assists. It spent 2 years studying the comet in unprecedented detail, deploying a lander and watching as it passed through perihelion. But 67P was a short-period comet, a regular visitor with a well-known orbit. Targeting a long-period comet would be more uncertain, but no less rewarding. One big reason for the interest is that long-period comets are thought to preserve material that's far older and less altered than what we find in the inner solar system. These icy bodies have remained in deep freeze for most of their existence, far from the warmth of the Sun and shielded from most radiation. Their internal chemistry especially if shielded from cosmic rays by a layer of dust or ice, could reflect the original makeup of the solar nebula, the cloud of gas and dust from which our solar system formed. Some scientists believe that long-period comets may also hold clues to the origins of water on Earth, or even the early delivery of organic compounds that played a role in the beginning of life. By studying their composition directly, we can test those ideas with much greater confidence. Another benefit of using these comets as practice targets is that they allow engineers to work out the many small but crucial details involved in chasing fast-moving objects in space. Navigation is one of the biggest hurdles. Even a slight miscalculation can cause a probe to miss its target by thousands of kilometers. Getting close enough to gather meaningful data, whether by flyby, orbit, or landing, requires careful planning and execution. Thermal conditions are another challenge. Comets can become violently active as they approach the Sun, releasing jets of gas and dust that can pose hazards to nearby spacecraft. Instruments must be shielded, trajectories must be adjusted, and sometimes close approaches have to be timed to avoid the most dangerous periods of activity. A long-period comet mission would provide a valuable test of these procedures, offering engineers real-world experience they could use when planning more daring intercepts of interstellar objects. While a long-period comet is technically a solar system object, its distance and history make it something of a stranger. Its chemistry may be different, its structure unusual, its ices containing molecules never before seen in a natural environment. It might even bring surprises, like a crust that resists outgassing, or a jet of material made from compounds not found on Earth. By collecting detailed data on a long-period comet's mass, rotation, porosity, and surface composition, researchers can build a better baseline for comparison. When the next Oumuamua-like object shows up, they'll have something to measure it against. Timing is everything. A good mission candidate would need to be found early, preferably before it crosses the orbit of Jupiter, so there's time to assess its path, design a trajectory, and launch a spacecraft with enough velocity to intercept. Once past that window, the chances shrink rapidly. Most long-period comets only appear once in human history. Miss your chance, and it's gone forever. Dedicated standby interceptors in space are being considered for asteroid defense and planetary science, but the same concept could work well for long-period comet interception. Long-period comets won't replace interstellar objects in terms of mystery or importance, but they offer a valuable training ground. They're rare, but not impossibly so. They give time to plan, but still offer the thrill of the unknown. And for scientists seeking a way to bridge the gap between current capabilities and the dream of chasing true interstellar visitors, they might be the perfect first step. Designing an Oumuamua chaser, propulsion and timing challenges. A typical deep space probe like Voyager or New Horizons uses chemical rockets to escape Earth's gravity and then coasts, using gravity assists to boost its speed. That works well for planets and even for the Kuiper Belt. But chasing something like Oumuamua would require much more. A chemical rocket alone would need to deliver an enormous amount of energy, far more than we've used for any previous mission. One idea is to use solid fuel or liquid fuel boosters just to get the spacecraft out of Earth orbit, and then add a powerful second stage to really crank up the velocity. Nuclear thermal propulsion has been suggested, since it could provide more thrust per kilogram of fuel. But that technology isn't ready for use today. It's still experimental, with decades of research and testing ahead before it could be launched safely and effectively. Ion drives and other electric propulsion methods are more efficient than chemical rockets, but they offer very low thrust. They're great for slow, steady acceleration over long periods, like the engines used on NASA's Dawn mission. But they're not ideal when you need to make up speed quickly. That makes them a poor match for the tight launch window and steep velocity curve that chasing an interstellar object demands. Solar sails don't require onboard fuel, so in theory they could keep accelerating for long periods. The Planetary Society's Light Sail project has demonstrated some of the basic principles, but the idea of using a solar sail to reach interstellar speeds remains largely untested. To make it work for a mission like this, the sail would need to be deployed perfectly, survive long exposure to solar radiation, and maintain a very precise trajectory. Even then, the sail would only be effective close to the Sun, where the light pressure is strongest. That means the spacecraft would need to get very close to the Sun first, possibly within Mercury's orbit, to get the best acceleration. Building a spacecraft, testing it, getting it ready for launch and aligning it with the object's trajectory in a matter of weeks would be nearly impossible with current infrastructure. So while several mission proposals were outlined in the months after Oumuamua's discovery, none were close to being ready in time. If another interstellar object were found in the future, and if it was still inbound when discovered, that would change the equation. Scientists could begin preparing immediately, choosing a launch window, calculating possible flight paths, and selecting a propulsion system that matched the object's speed and direction. But even then, the options would be limited. The launch window is everything. If you launch too early, the spacecraft may not have enough speed to catch up. If you launch too late, the object will be too far away to reach with any practical engine. Missing the window by just a few weeks could mean the difference between a successful intercept and a complete miss. And unlike planetary missions, which can often wait for the next alignment a few years later, there is no second chance with an interstellar object. To meet this kind of deadline, mission planners are looking at modular spacecraft that can be built and kept in ready state on Earth. The idea is to have most of the hardware ready ahead of time, so only the final course calculations and launch procedures need to be done after a target is spotted. That urgency is part of what makes the challenge so unique. Most space missions have years or even decades of planning behind them. A mission to chase something like Oumuamua would need to be planned in weeks or months. That means automating as much of the process as possible, using onboard systems to calculate approach angles, manage course corrections, and handle unexpected events. AI-guided navigation could help keep the spacecraft on track without constant input from Earth, which is essential when signals can take hours to travel back and forth. This is why some are now focusing on building readiness for the next time. They're proposing early warning systems, fast response mission templates, and infrastructure that can be activated quickly when the next interstellar visitor shows up. It's a different mindset from the slow and steady planning that usually defines space exploration. But it may be necessary if we want to explore objects that aren't part of our solar system. The propulsion and timing problems are not unsolvable, but they do force a new kind of thinking. Space agencies and private companies may need to work together, share resources, and create modular systems that can adapt on short notice. Mission success will depend not just on speed, but on flexibility, the ability to shift gears quickly and launch when the moment arrives. Pre-covery archives, mining old data for lost interstellar guests. Long before astronomers had any idea that Oumuamua was slicing through the solar system, it was already visible, just too faint, too fast, and too strange to stand out. The telescope surveys that might have caught it earlier had already taken the pictures, but the object blended in with the background noise. It's not that no one was looking, it's that no one knew what to look for. That has led scientists to go back to those old images with a new mindset. This process is called pre-covery, short for pre-discovery recovery, and it's become a key part of understanding fast, rare objects from interstellar space. Pre-covery is about mining existing data, not making new observations. Telescopes around the world take countless images every night and many of those images end up in long-term digital archives. Some of these records date back decades. They include wide-field survey plates, deep exposures of distant galaxies, and images meant for entirely different projects. In some cases, they are photographic plates that have been digitized from the 1950s or even earlier. The value of this mountain of data isn't just in what was targeted, it's in everything that was captured by chance. After Oumuamua was first detected in October 2017, scientists wanted to trace its path backward. If they could find earlier images of it before the discovery date, they could refine its orbit and maybe even get a better estimate of where it came from. It would also stretch the time baseline, allowing for improved models of its motion through the solar system. But searching through archives for such an object isn't easy. Unlike stars and galaxies, which are fixed or slowly drifting, interstellar objects move quickly. They don't follow the slow, looping paths of asteroids or comets. Their paths cut across the solar system at steep angles. This makes them hard to find in records that weren't designed to detect that kind of motion. The search process usually starts with known data, like the time and place of the first detection. From there, orbital mechanics can provide a rough idea of where the object might have been in the past. But there are uncertainties. Small changes in speed, angle, or light curve can throw off a prediction by a wide margin. So instead of a single path, scientists look along a possible corridor. Within that corridor, they examine archived images from different telescopes, checking to see if anything matches the expected track. It's slow, detailed work. But sometimes a streak or smudge turns up, just one faint dot or line that matches the trajectory and speed. That's how earlier images of Oumuamua were found. A few exposures taken before its official discovery showed the object as a dim spot moving through the sky. These weren't enough to tell its entire story, but they helped anchor its trajectory and narrow down the range of its possible origin. The earlier an object is found in old images, the more precise its orbit becomes. With every added data point, uncertainties shrink, and researchers can trace the object farther back in time. In the years since, Pre-covery has expanded from just being a cleanup tool to a method of discovery in its own right. For example, after Syneos 2014-1-8, scientists used pre-covery methods to confirm the object's high speed and possible interstellar origin. They didn't have direct telescope images of it entering Earth's atmosphere, but by reprocessing sensor data, they were able to link its trajectory with satellite detections and atmospheric energy signatures. These indirect methods function as a kind of pre-covery, filling in the missing information after the fact. The value of pre-covery also lies in the long-term storage of sky surveys. Projects like the Sloan Digital Sky Survey, Pan-STARRS, and even amateur observatories have contributed to databases of sky images that stretch back many years. Some of these surveys update their image catalogues regularly, improving sensitivity and resolution. With improved search software and better computing power, it's now possible to comb through thousands of frames in a fraction of the time it would have taken just a decade ago. Objects like Oumuamua weren't the focus of these archived images. They happened to pass through the field of view while the telescope was doing something else. That randomness turns into a strength when looking for interstellar visitors, because it means coverage isn't biased toward a fixed search pattern. In theory, an interstellar object could appear in hundreds of images taken over the years, completely unnoticed. Noise in the data, satellite trails, camera glitches, or even cosmic rays can all produce streaks that look like moving objects. A single frame isn't enough. Scientists often need to confirm motion across multiple images and make sure it aligns with what would be expected from an actual object moving through space. With the right alignment, a pattern emerges. The dream scenario is to find an image of an object like Oumuamua months or even years before its discovery. That would give a massive boost to orbital accuracy and allow scientists to work backward to its point of origin with far more confidence. It could even connect the object to specific stellar neighbourhoods or birthplaces, maybe even debris fields around dying stars, young solar systems, or interstellar clouds. Those backward projections would also help refine future search strategies, giving hints about where to expect other incoming objects. Pre-covery rewrites our understanding of what has already happened. Every time a new hyperbolic object is discovered, the hunt begins again. Researchers take the known data and plunge into archives, looking for earlier signs. Each faint streak pulled from a dusty image expands the interstellar record, even if only by a few seconds of exposure time. Over years and decades, those seconds add up. They become the hidden biography of an object that travelled for eons, crossing the galaxy, arriving unnoticed, and only now being recognised for what it was. Mission-ready spacecraft, smallsat swarms for rapid response. In the world of space exploration, the concept of a flagship mission typically conjures images of massive spacecraft carefully designed over many years, costing billions of dollars and requiring decades of planning, construction, and testing before being launched. These missions, such as the Hubble Space Telescope or the Voyager probes, are monumental undertakings, often requiring the coordination of vast teams of scientists and engineers. But in recent years, the rise of smaller, cheaper spacecraft, known as smallsats or small satellites, has begun to change the landscape of space exploration. These miniature satellites, which can be assembled in a fraction of the time and at a fraction of the cost of traditional space missions, have opened up new possibilities for rapid response exploration. One of the most exciting prospects for smallsats is the potential to create swarms of these tiny, inexpensive spacecraft that can be launched on short notice. Instead of waiting years for a massive flagship mission to be developed, a swarm of smallsats could be launched within days, providing immediate reconnaissance and data collection. This is a stark contrast to the traditional timeline of space missions, which can take several years of development and design before even the initial stages of a mission begin. A swarm of smallsats would consist of multiple small satellites working together as part of a coordinated network. These satellites could be launched together or individually, each with its own specific task or instrument. Together, they would form a highly flexible and efficient system capable of gathering a wealth of data from various angles and perspectives. This approach offers significant advantages, particularly when it comes to unexpected events that require a swift response, such as the detection of a fast-moving interstellar object. The ability to launch and deploy a swarm of smallsats in a matter of days or weeks is made possible by several key technological advancements. First, the development of small modular spacecraft has drastically reduced the cost and complexity of building space probes. These smaller satellites are built using off-the-shelf components, which can be assembled much more quickly and inexpensively than the custom-built systems used for traditional missions. Additionally, the miniaturization of scientific instruments has made it possible to pack a wide array of sensors and tools into small, lightweight packages, allowing for a level of scientific versatility that was previously impossible at such a low cost. Because they are smaller and less expensive, they can be designed to address a wide range of mission objectives. In the case of an interstellar object passing through our solar system, for example, each smallsat in the swarm could be tasked with a specific role. One could focus on imaging the object from a distance, while another could study its chemical composition, and yet another could analyze its motion and trajectory. Together, these smallsats would provide a comprehensive set of data, offering insights into the object's physical properties, its origins, and its potential impact on our solar system. A swarm of smallsats could be deployed with the ability to adapt and change course as new information becomes available. This agility would allow for a much more dynamic response to unforeseen events, ensuring that humanity is not caught off guard by a sudden, significant discovery. Moreover, the small size of these spacecraft would allow for greater diversity in the kinds of observations they could make. A traditional flagship mission typically uses a single spacecraft to conduct a variety of experiments and observations, but the sheer size and complexity of these missions can limit the number of instruments and the types of data that can be collected. Smallsats, on the other hand, can be specialized, each focusing on a specific aspect of the target. A single swarm could have multiple spacecraft with distinct scientific tools on board, such as cameras, spectrometers, magnetometers, or even communications equipment, all working together to gather a more comprehensive dataset. These missions also offer the potential for redundancy and resilience. In traditional missions, if one spacecraft malfunctions or fails, the entire mission could be compromised. With a swarm of smallsats, however, the failure of one satellite would not bring down the entire mission. The remaining satellites in the constellation could continue to gather data, and the system could be reconfigured to make the most of the remaining resources. This redundancy is particularly valuable when dealing with unknown or unpredictable targets, where the risks of failure are higher. The low cost of building and launching individual smallsats means that even if a mission were to fail, the financial loss would be relatively small compared to a flagship mission. This makes the concept of rapid response missions much more feasible, especially in situations where a sudden, unforeseen event could present an opportunity for scientific discovery. Smallsat missions also benefit from the rapidly growing space commercialization sector, which has driven down the cost of launching payloads into space, making these kinds of missions increasingly affordable. One of the challenges of using smallsat swarms for space exploration is the complexity of managing and coordinating the constellation of satellites. While each satellite in the swarm is designed to operate autonomously, ensuring that they work together in a coordinated and efficient manner requires sophisticated algorithms and control systems. These systems must be capable of adjusting the positions of the satellites in real time, responding to new data and unexpected changes in the target's behavior. Moreover, data collected by the swarm must be processed and transmitted back to Earth, which requires robust communication systems that can handle the high-volume data streams generated by multiple satellites working in parallel. Despite these challenges, the potential benefits of smallsat swarms are undeniable. These constellations offer a new paradigm for space exploration, one that is more flexible, cost-effective, and responsive to unforeseen events. Whether it's studying a fast-moving interstellar object or monitoring an incoming comet, a swarm of smallsats could provide the data we need with unprecedented speed and precision. This approach also holds promise for other types of missions, such as planetary exploration, asteroid mining, or even the study of distant exoplanets. With smallsats, we could deploy large numbers of spacecraft to study a particular target from multiple angles, gathering far more data than a single spacecraft could ever hope to provide. The flexibility and scalability of smallsat swarms make them an ideal tool for a wide range of space missions, offering the potential for rapid, large-scale scientific discovery. Implications for exoplanetary science and habitability. Understanding what worlds beyond our solar system are made of has always been one of the biggest goals of space science. With hundreds of exoplanets discovered every year, some gas giants, some Earth-like, some wildly unfamiliar, we now know that our solar system is not unique. But while telescopes can give us light curves, orbital paths, and even hints of atmospheric chemistry, there's a serious limit to how much we can learn from a distance. Interstellar objects are messengers, physical samples that can reveal what materials formed around other stars. This matters because planet formation is messy. The process starts in a swirling disk of gas and dust that spins around a young star. In that disk, particles stick together, clump into pebbles, and grow into larger chunks. Over time, they collide, merge, and scatter. Some become planets, others moons or asteroids. But a lot gets ejected, especially in the chaotic early stages. These ejected bodies may come from the outer regions of those systems, the zones rich in volatile compounds like water, carbon monoxide, and methane. If those ejected bodies escape their original stars and drift across interstellar space, we might get a chance to intercept them. By studying them, we get something that no telescope could ever offer: the exact mix of elements, minerals, and ices that formed in another protoplanetary disk. It's a sample of planet-forming material shaped by a different star, under different heat levels, with different metallicity and dust-to-gas ratios. This helps refine or challenge our existing models of how planets form in general. Are rocky planets like Earth rare or common? Do gas giants form differently around larger stars? What minerals dominate in disks where the temperature curve is steeper or the star's UV output is higher? A single object could hold chemical clues that push us closer to answers. When we look at Oumuamua and 2I/Borisov, their differences tell us something already. Borisov looked like a more traditional comet. Spectral data showed cyanide and carbon monoxide, both familiar from comets in our own solar system. This implies that wherever it came from, conditions were cool enough to preserve volatile ices, and that organic chemistry wasn't that different from what we see here. That kind of data lines up with what we expect from systems like our own, possibly indicating that water-rich outer regions and organic-rich ices are a common feature in planetary disks. Oumuamua's odd behaviour tells us that material and structural diversity in other systems could be much wider than we've guessed. One key area of interest is water. Finding water in interstellar objects and learning where it is stored and how it behaves can help explain how common wet planets might be. If every system throws off water-rich bodies in the early stages, then the delivery of water to rocky planets like Earth could be a universal process. It would suggest that oceans, rivers, and even life might not be rare at all. Beyond water, there's the role of organics. Long-chain carbon molecules, some resembling amino acids or the building blocks of RNA, have been found in comets from our own system. If interstellar objects also carry similar compounds, that would support the idea that life's ingredients are widespread in the galaxy. And if their chemistry turns out to be totally different, based on alternative pathways or containing molecules that are unstable in our environment, it could open new ways of thinking about how life might evolve elsewhere. The isotopic ratios, like the mix of deuterium to hydrogen or the balance between carbon-12 and carbon-13, can differ based on where in the protoplanetary disk the material formed, and on how long it stayed in cold or warm regions. Matching these values against what we see in comets and meteorites here lets scientists build a kind of chemical fingerprint for other solar systems. If a sample shows unusually high levels of heavy isotopes, it might have formed near the outer edge of a disk or in a dense, cold molecular cloud before getting swept into a young planetary system. These fingerprints could also link to the age of the system. Some materials, like radioactive isotopes, decay over known timescales. Finding traces of those in interstellar samples can help estimate how long the object has been drifting through space. That in turn could help reveal whether it was ejected early in its star's formation or much later during a period of instability. Even the structure of the dust, whether it's loose or tightly bound, whether it's coated with carbon films or iron particles, can inform models of how solid bodies come together. Different stars have different outputs of radiation and stellar winds. That affects how dust grains collide and stick. It also affects which materials survive close to the star versus in the distant regions. Getting actual samples from those regions gives scientists real data to check their models against. These kinds of data are especially valuable because direct study of exoplanets is so hard. Most of the ones we've found are detected by how they affect their stars, by dimming the light during transits, or by causing tiny wobbles through gravity. A few have atmospheres that we can study with instruments like the James Webb Space Telescope. But surface material, core composition, and deep chemistry remain completely out of reach. An interstellar object may not tell us what a full planet is like, but it can show us what planets are made of and how their building blocks behave. Quantum communication beacons, eavesdropping on hypothetical alien signals. Among the stranger ideas to come from the search for extraterrestrial intelligence, or SETI, is the thought that alien civilizations, if they exist, might not be using radio waves to communicate at all. For decades, the SETI Institute has focused on scanning the sky for electromagnetic signals, hoping that a far-off society might be broadcasting in a way we can detect. But there are limits to that method. Radio waves take years to cross space. They can be distorted by dust, absorbed by gas clouds, and weakened by distance. And they make noise. Any powerful radio signal might alert other civilizations to your presence, which could be dangerous. So the question arises, what if more advanced species use something else? Something quieter, faster, and harder to intercept? That's where the idea of quantum communication beacons enters the picture. This theory, still speculative but grounded in real physics, imagines that an interstellar visitor, like Oumuamua, might be a delivery system, a carrier for quantum-entangled particles designed to act as a relay station. Instead of sending signals across empty space, which takes time, a device on board could use quantum entanglement to link information between 2 points instantly. This kind of communication wouldn't involve traditional waves at all. It would rely on the strange, counterintuitive properties of quantum mechanics. Quantum entanglement is one of the most baffling ideas in physics. When two particles are entangled, they become connected in such a way that the state of one affects the state of the other, no matter how far apart they are. Change one, and the other responds instantly. It doesn't seem to follow the rules of classical physics. In recent years, lab experiments have shown entanglement working over distances of dozens, even hundreds of kilometers, with no delay. The particles behave as if they are part of a single system, despite being physically separated. The idea of using entanglement for communication has fascinated scientists and engineers. In principle, if two parties shared entangled particles, they could exchange information without sending a traditional signal through space. That could make quantum communication incredibly fast and secure. Nothing moves between sender and receiver in the classical sense, so there's no wave to intercept. There's no signal to block. The communication is instant in theory and private. For SETI thinkers, this raises a big question. If an alien species had developed this kind of technology, would we even know they were talking? One hypothetical proposal is that an object like Oumuamua could serve as a physical relay, a node in a larger communication grid. Imagine a civilization that seeds its galaxy with such objects, each containing onboard systems to manage entangled links or refresh entanglement between distant parties. Instead of using Earth-like antennas or optical lasers, the system could operate quietly, distributing particles as needed, while appearing inert to casual observation. From the outside, a relay node might look completely natural, but inside, it could house carefully engineered systems designed to interact with quantum states at a level we have yet to master. While there's no evidence that this is what Oumuamua is, or that any such beacons exist, the concept itself is compelling because it shifts the entire framing of SETI. It asks what types of communication might not leave an obvious trace. Quantum communication could be fundamentally undetectable by current radio telescopes. It could bypass the assumptions that have guided SETI work for decades, such as the idea that all civilizations would use the electromagnetic spectrum in the way we do. Still, there are challenges with using entanglement for messaging. In practical terms, entangled particles can't be used to send information by themselves. The outcome of measuring a quantum state is random. To actually transmit a message, the entangled states have to be combined with classical communication. In most quantum communication methods today, such as quantum key distribution, entanglement is used to establish a secure link, but not to transfer content instantaneously. The content still travels at light speed or slower. That technical detail has led many scientists to be skeptical of faster-than-light communication using quantum mechanics. But the theory continues to evolve. Some researchers suggest that there may be ways to sidestep these limitations using clever architectures, hybrid protocols, or as yet undiscovered quantum effects. If a highly advanced civilization had found a way to do this, perhaps using forms of matter or states of energy we don't yet understand, it would be operating on a level far beyond current human capability. Even if not transmitting messages instantly, such a beacon could be maintaining entangled particle pairs with other devices scattered across the galaxy. A small probe, launched thousands of years ago, could travel vast distances, arriving silently in a new system, holding a cache of stored entangled particles ready to be connected with others. That would allow it to act like a router or buffer in a massive interstellar quantum network. It wouldn't need to stay in one place or have massive energy supplies. Its main job might be to quietly maintain coherence among its onboard particles, perhaps refreshing its link through onboard atomic systems or advanced photonic loops. There would be no radio output, no laser beam, no heat signature that reveals active transmission. Most of the processes would take place at the particle level. Quiet, subtle shifts in quantum states, isolated from thermal noise. From our point of view, the object might appear inert. Researchers have started thinking about how to test for such possibilities. One idea is to analyze the quantum noise of nearby regions of space, looking for unusual correlations that can't be explained by standard physics. Others suggest placing ultra-sensitive quantum sensors aboard future spacecraft, allowing them to scan passing bodies for unexpected fluctuations in entanglement-sensitive materials. SETI might eventually expand to include quantum observations, searching not just for noise or pulses, but for absences, for coherences, for structures that suggest manipulation at the smaller scale. If civilizations really are using quantum communication, it could mean the galaxy is already full of conversations we'll never hear. Not because we're being excluded, but because we're not listening in the right way. Our current tools, built to detect leaks and broadcasts, might be tuned to a form of technology that advanced species left behind long ago. They may not be shouting across the void, but whispering through quantum threads. There's also the possibility that these beacons aren't still in use. Like old satellites from the Cold War drifting in orbit around Earth, these could be relics, leftover infrastructure from a long-gone civilization. Their entangled particles might have degraded. Their systems might have failed. But the devices remain, mute but still complex, waiting for someone to notice. If one were found and closely studied, it could provide a different kind of discovery, not just about communication, but about the presence of intelligence that once was. From antennas to algorithms, from lasers to qubits, every new frontier in physics becomes a new lens through which to ask, if someone out there is trying to talk, how would they do it? And what will it take for us to finally hear them? And with that, today's journey comes to an end. What other mysterious objects would you like to hear about? Comment down below, and if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.